Hello friends, welcome back to my channel Key to Learn. In this video, we are going to learn about Python 3. This is chapter 2 of the Python 3 Masterclass.
Hi, and welcome to this section on variables. So in this section, we're going to look at memory references. And in that context, we'll take a look at what variables really are. We tend to think of variables as names that we can assign values to, that we can read values back from. But there's a little more to it than just that. And so we'll look at variables in the context of memory references. We'll also look at memory management. And in particular, we'll take a look at something called reference counting. And we'll also look at something called garbage collection. Now, these two things are not quite the same thing. And we'll look at the differences between those two. And we'll also take a look at why it's important for us to understand that. Next, we'll look at dynamic versus static typing. Now, Python is a dynamically typed language, as opposed to other languages like Java or Swift or C++, which are statically typed languages. After that, we'll look at mutability and immutability. Now, you probably already are aware of these concepts, but immutability has some little wrinkles to it that we'll examine in this section. Then we'll look at something called shared references. This is where variables share the same area in memory, they share the same object. And so we'll take a look at what that means in terms of variables and also in terms of functions. When we call functions and pass variables to them, what's going on behind the scenes. Then we'll look at variable equality. Now, we tend to think of variable equality as, well, if they have both the same value, they're equal. But there can also be other instances where maybe we're not talking about the values, but something else. So we'll take a look at variable equality, again, in the context of memory references. And then lastly, we'll look at the fact that in Python, everything is an object. So, the variables that we're used to, like integers and strings and lists, are all objects, but everything else is an object too. Functions are objects, right? Classes obviously are going to be objects when you instantiate them, but classes themselves are actually objects as well. So we'll take a look at that concept in Python, and this actually will follow through in all the remaining sections of this course as well. So this is kind of a foundational step that we need to take. All right, thanks, and I'll see you in the next lecture. Hi, and welcome to this section on variables and memory references. And in fact, we'll see very shortly that variables are memory references. So first, let's talk about memory a little bit, and we'll do a conceptual diagram of memory. And we can think of memory as a series of slots or boxes that exist in our computer, and we can store and retrieve data from those slots. We can also compare it to the mail system. Now, when you send a letter to somebody, you usually have to write an address on that letter. And that address corresponds to a unique mailbox somewhere in the world. And by writing that address, you make sure that the contents of your letter is delivered to that mailbox. And it's pretty much the same in computers. And with memory, we need a unique address for each of those slots. And typically they're just numbers. So we can number them arbitrarily, 1000, 1001, 1002, and so on. And those are called memory addresses. Now, when we store data in memory addresses, we may actually use more than one slot at a time. Certain amounts of data will fit nicely inside a single slot, but those slots have a finite amount of space. But as long as we know where the object starts in memory, that's good enough. And so, for example, object number 1 is stored at address 1000. Now it overflows into another memory address, let's say 1001. Same thing with object number 2. Object number 2 starts at memory address 1002 and overflows into 2 more of those slots. Object number 3 happens to fit precisely in 1 slot, and it's at address 1005. And that is called the heap. And storing and retrieving objects from the heap is taken care of for us by something called the Python Memory Manager, which we'll look at in more detail in a later lesson. So let's take a look at what happens when we write a line of code such as myval1 equals 10. So let's bring back our conceptual diagram of memory, and here we have those empty slots. So when we execute the statement myval1 equals 10, the first thing Python does is it creates an object in memory at some address, let's say 1000, and it stores the value 10 inside that object. And myval1 is simply a name, an alias if you will, for the memory address where that object is stored, or the starting address of the object if it overflows into multiple slots. And so myval1 is said to be a reference to the object at address 1000. Now you'll note myval1 is not equal to 10. myval1 in fact is equal to 1000 in this case. But 1000 represents the memory address of the data we're actually interested in. So as developers, when we write code, we kind of think myval1 is equal to 10. And for all practical purposes, it is. But we have to remember myval1 is not equal to 10. It is a reference to an object at that location. Similarly, if we write myval2 equals hello, it first gets created and stored somewhere in memory, let's say at address 1002. And if it overflows into more slots, that's fine. And myval2 now becomes an alias or a reference to that memory address. And we say that myval2 references the object at address 1002. So again, it's kind of important to understand variables in Python are always references, and they're references to objects in memory. So in Python, we can find out what the memory address is of a variable by using the ID function. Now, it's not something you will typically be using as you write Python programs, but we will be using it quite a bit in order to understand what's happening in the Python programs we run, and especially what is happening to variables as we pass them along in our code throughout their lifetime. It is important to understand what's really happening. So the ID function will return a base 10 number, and if you want, you can convert that to a hex number by using the built-in hex function in Python. So for example, if we have a equals 10, we can find the hexadecimal version of the memory address of a by printing out hex of ID of a. So let's take a look at a quick example in Python and see how that works. Okay, so let's create a variable. Let's say myvar equals 10. So now we've created this variable. And remember, what's really happening is that 10 was saved somewhere in memory, and myvar is now a reference to that object. Now we can print out myvar, and we can see it returns 10. Now, what actually happened is that Python looked at myvar. It then looked at what is the memory address that myvar is referencing. It found that memory address. It went to the memory, retrieved the data from memory, and then brought it back so that we can display it in our code. So we can look at the memory address by using the ID function. So we can look at the memory address of myvar by using the ID function. And there we go. It's this big number there, 17183488528. Now, when you run this code, you probably won't get the same number, right? Because the memory addresses will be different. In fact, if we rerun this code later on, we'll have a different memory address. We can also print the hexadecimal version of the memory address by using the hex function, passing it the ID, which is the decimal version of the memory address of my var. And when we run that, we get a slightly shorter number, which is why I like using the hex versions. So 666BEAF0. Now let's do another one. Let's do greeting equals, let's use a string this time. Okay, so we have greeting equals hello. We can print it out. Okay, so we'll print it out. There we go. It retrieved the data that was at the memory address referenced by greeting. Now, what is the memory address? Well, we can look it up. And this big number here, which as you can see is different from the memory address of my var. If we want the hex version, we just do hex of ID of greeting. And there we go. That's the hex number for the memory address that greeting references. All right, so bottom line, variables are just memory addresses. They're not actually equal to the value we think they're equal to. Logically, we can think of it that way, but in real terms, they're memory references. All right, thanks for watching, and I'll see you in the next video. Hi, and welcome to this video on reference counting. So if we write this line of code, my var equals 10, remember what's actually happening is Python is creating an object of type integer with a value of 10 at some memory address, let's say 1000 in this case. And my var is a pointer to that object. My var is actually the reference, the memory address of that object. In this case, let's say 1000. So we can start keeping track of these objects that are created in memory. We can keep track of them by keeping track of their memory address and how many variables are pointing to them. How many other variables in our Python code are pointing to that same object. So in this case, we only have one reference. And so the reference count for that memory address is 1. But let's say we write this other line of code. Other var equals my var. Now remember, we are dealing with pointers, right? We're dealing with memory addresses, references. When we say other var equals my var, we are not taking the value 10 and assigning it to other var. We're actually taking the reference of my var and assigning that reference, 1000, to other var. In other words, other var is also pointing to that same object in memory. So it's really important to understand that distinction. We do not have two separate objects of value 10 and my var points to one and other var points to another one. No, when we say other var equals my var, we're actually sharing the reference. And so the counter in this case will go up to 2, right? So the reference count is now 2. Now let's say that my var goes away. Either it falls out of scope, or maybe we assign it to a different object in memory, maybe even assign it to none. Then that reference goes away, and the reference count goes down to 1. And let's say other var also goes away. So at some point in time, maybe it goes out of scope. Now there is nothing left, and the reference count therefore drops down to 0. At that point, the Python memory manager recognizes that and says, oh, okay, there's no object left. I don't need it anymore. There are no references left. I don't need this anymore. And it throws away the object. And that object goes away, and the space it used up can now be reused by Python when it's running our program. So this is called reference counting, and that's something that the Python memory manager does for us. We don't have to worry about this. It's doing it automatically, right? But just keep in mind, that's what's going on with the reference counting and when we create variables. And then later we'll look at something else called garbage collection, which is related to this. So before we get to the code, we're going to look very quickly at how we can find the reference count of a variable in Python. The sys module has a getRefCount function that we can use, and we call it by sys.getRefCount, and we pass in the variable name. So we put the variable name in there, and we'll look at that closer down the road, but what's happening here is we're passing a reference to my var, right? We're passing that reference. So when we pass my var to getRefCount, it's actually creating another reference to that same object in memory, right? So there's a kind of a downside to using getRefCount in that it always increases the reference count by 1, because simply the act of passing my var to the function creates another reference to that same variable, because variables are passed by reference in Python. And again, we'll get to that in more detail later. So there is another function we can use that doesn't have that drawback. It's in the C types module. It's certainly at a lower level. It's basically starting to dig down into the C libraries. And this is just what it is, ctypes.clong from address, etc. The difference here is that we're passing the memory address, so ID of my var. So because we're passing the memory address, not the reference, we're passing the actual integer value, let's say 1,000 in the example we had before, it doesn't affect the reference count. And so this is a truer, more exact count of the number of references. So let's switch to code and take a look at all that in some detail. We'll start by looking at the sys module, and we'll use the getRefCount from that module first. So we'll have to import it. So let's import sys. Then we should create a variable, and I'm going to use a list, and we'll see in some upcoming lessons why I'm not using an integer here, because you might be surprised at the answer we get. So I'll create this variable a. Now remember, what does it mean by saying a equals 123? 123 was created as an object in memory at some memory address, which we can find. Let's call it, well, actually, let's just print it out. Okay, it's that memory address. Now, when you run this code, you'll get a different number. So we have this object created in memory, and a points to that memory address. A is a pointer. So now we can use the sys.getRefCount, and getRefCount expects the variable name as its parameter. So a in this case. Now what this means is that we're passing a to getRefCount, and its argument is taking the same reference that a is telling it. So it's going to point to the same object in memory. So really our reference count is going to become 2 when getRefCount runs. And indeed that's what we get, 2. So you can use getRefCount, it's not an issue. Just remember to subtract 1 from that answer, because the simple fact of passing a into it, of passing the variable into it, has increased the reference count by 1. So if you don't want to have to deal with that, then we can use the ctypes library. So we have to import ctypes first. And then we have that long expression that I showed you in the slides. So I'm going to create a wrapper function called refCount. That's going to take the address. And if you want to use annotations, we can specify that the address is going to be an integer. And it's going to return that. Okay, so ctypes.clong.fromAddress of the address, which is the argument here, the first argument in the function, dot value. Okay, that way we don't have to type that whole long expression every time. So now we can get the reference count of a, but we have to pass it the memory address. So we can do ref count ID of a. And we get a reference count of 1, which is what we expect. Now you might be thinking, like, wait a minute. You said that we get a ref count here of 2 because we passed a into this function. Aren't we doing the same thing here? We're passing a inside this function. Why isn't the reference count 2? Well, what's happening is ID of A is getting evaluated first. So indeed, when we call ID of A, when ID is running, then the reference count to that memory address, 183.10115, is 2, right? Because it's got a reference. We passed it as a parameter. So the argument of that function has a reference to that same object in memory. So at that point, the reference is 2. But ID then finishes running and returns the memory address, okay, that we have up here. So by the time we call ref count, ID has finished running and it has released its pointer to that memory address, right? That pointer's gone. So now the reference count is indeed back to 1, right? So this is no different than doing it this way. Let me copy the memory address that we just took, pass it in here, and we get ref count of 1. So that's exactly the same thing, right? So don't be confused by the fact that the ref count is 1 even though A is here. That's because by the time ref count is called, ID has finished running, it has already returned the memory address, and therefore it has released whatever reference it had to that memory address. Okay, so now we have A equals 1, 2, 3. Let's go ahead and say B is equal to A. Okay, so B equals A. And now we can call ref count again on the ID of A. Well, before we do that, let's take a look at the ID of B. Let's just make sure that it is indeed pointing to the same location in memory, and it is. As you can see, A and B are both pointing to the same location in memory. So our reference count should be 2. So we can say ref count of the ID. Now we can use either A or B, they're identical, and we can see the ref count is 2. We can go further and say C is equal to A, and we can look at the ref count of the ID of A, and again now we have a reference count of 3. Now if I change C to something else, if I say C equals 10 for example, now if I do ref count of ID of A, you'll see the ref count is back down to 2. And if I set B equal to maybe none, okay, then we can do ref count of ID. Now I have to use A, I can't use ID of B because that would be a different object, right? The ID of B, let's put that in quick, ID of B, as you can see, is not the same as it was before. That's because we've set B equal to none, which is actually a real object that has an existence in memory that it's pointing to. So here, if I look at the reference count of A, however, I get down to 1. Now what I'm going to do is I'm going to store the memory address. So I'm going to say A ID equals ID of A. Then I'm going to set A equal to none, and then we're going to call ref count on A ID. Now the reason why I'm doing that is because I cannot call ref count of ID of A after I've set A equal to none. I still want to look at this original memory address, okay? So now the answer you're going to get here may very well be different than the answer I'm going to get. And I'll get into that into a lot more detail later. But let's take a look. So I still have a reference count of 1 for A. That's just weird, for that old memory address. Okay, so maybe I'll run it again. And now it's 0, okay? Or if I run it again, ooh, now it's some weird value. All right, so this is because we are using that C library. So we are actually, in this code, we are specifying the memory address we're interested in, okay? Which was this memory address over here. When the last reference to that memory address was dropped, when we set A equal to none, remember what happens. The memory manager frees up that memory address, essentially tosses away the object, and that memory address becomes available for something else. And that's what we're seeing here, right? So typically in Python, we don't work with memory addresses. I'm just doing that as an illustration and just to try and understand what's going on behind the scenes. But what's happening here is that what is stored at that memory address, once I set a equal to none, we don't know what's stored in there. It's probably just junk, right? Or maybe something else. So in Python, we never deal with memory addresses directly. It's very dangerous to do that. And as you can see here, you can't rely on that. Okay, so we've got to be careful. Again, just for illustration purposes, you're never going to have to use that in Python, unless you're trying to debug stuff or figure out, what's going on, especially with things like memory leaks. All right, so I'll see you in the next lesson where we'll talk about garbage collection, which is related to reference counting, but it is not the same as reference counting. It's a different process that Python utilizes to also keep up with cleaning up the memory and keeping things freed up so we don't have memory leaks. Thanks, and I'll see you in a bit. Hi, and welcome to this lesson on garbage collection. Now, in the previous video, we took a look at something called reference counting. So remember what reference counting is. As we create objects in memory, Python keeps track of the number of references we have to those objects. There could be 1 reference, 2 references, 3 references, but no matter what the number of references is, as soon as that reference count hits 0, the Python memory manager then reclaims, it destroys that object and reclaims the memory. So that's called reference counting. But sometimes that just doesn't work. And in particular, we have to look at a situation called circular references. So what are circular references? Well, let's take a look at an example. Let's say we have a variable, myVar, and let's say that myVar points to object A. So far, it's exactly what we've seen. If myVar goes away, if we point it to another object or to none, then the reference count of object A goes from 1 to 0, and the Python memory manager at that point destroys the object. So far so good. But let's suppose that object A has an instance variable, let's say var1, that points to another object, let's say object B. So at this point, what happens if we get rid of that myVar pointer? Let's say we point it to none. Then the reference count of object A goes down to 0. Now the reference count of object B is still 1 because object A is pointing to B. But the reference count of object A has gone down to 0, and so by reference counting, it will get destroyed. Once it gets destroyed, object B's reference count also goes down to 0, and it gets destroyed as well. So by destroying myVar, by removing that reference, the Python memory manager, through reference counting, will get rid of object A and B. So far, no problem. But now, let's suppose that object B also has an instance variable, let's say var2, and var2 points back to object A. Now we have a circular reference. So what happens if we get rid of the myVar reference? So if that goes away, then the reference count for object A, you will notice, is 1 still, right? It was 2 because myVar was pointing to A, B was pointing to A, so A had a reference count of 2. myVar went away, right? So the reference count now on A is 1. It's not 0. And the reference count on B is also 1 because A is pointing to B. So in this case, reference counting isn't going to destroy either A or B. It can't, because they both have references. They both have a reference count that is non-zero. And that is called a circular reference. And because the Python memory manager cannot clean that up, if we were to leave things as is, we would have a memory leak, right? Because myVar went away, but object A and B didn't. And there's no way that they'll get destroyed. Not through reference counting. So that's where the garbage collector comes in. The garbage collector will look and will be able to identify these circular references and clean them up. And so the memory leak goes away. We we do get cleanup. So the garbage collector can be controlled programmatically using the GC module. There's a built-in module to Python called GC for garbage collector, where you can interact with the garbage collector and you can even modify its behavior. So by default, garbage collection is turned on. Now you can turn it off. So you can turn it off, but you really have to be absolutely sure that your code is not creating circular references, because if it does, you will end up with memory leaks. And it's very easy to create circular references and, without even knowing that you've created that circular reference. So be very, very careful if you do turn it off. Now, why would you want to turn it off? Well, it's really just performance reasons. The garbage collector is something that runs periodically, by default about every minute or so, and it has to identify these circular references, so obviously it takes a little bit of, computing power to do so. And so you may want to turn it off, but this is really more advanced and you have to be careful. I would just leave the garbage collector turned on unless you have a specific need to turn it off. So it runs on its own. If it's turned on, you can turn it off. You can also call it manually, and you can also interact with the garbage collector to see what's in there that needs to be cleaned up, especially if you've turned it off, and do your own cleanup. And so some people do that. There's other ways you can also avoid having to do your own cleanup. You can use weak references. There's a variety of things that you can do. We'll look at weak references when we get to the sections on object-oriented programming. But for now, just be aware the garbage collector is there to really clean up circular references. It's turned on by default, and you really should leave it on. So in general, it works just fine. But as always, there's a caveat. It doesn't always work. But this really applies to Python versions of less than 3.4. So as long as you're using Python 3.4 and above, 3.6 as of this recording, then you're fine. What was happening before is that if even one of the objects in the circular references had a destructor, so for example, if you're creating your own class, you can create a constructor for the class, yes, but you can also create a destructor. Now the destructor is code that you run when you're destroying the object. And typically you might put things in there that might be cleaning up files, maybe deleting files that you created that were needed during the duration of that object, maybe closing a database connection, whatever it is. And you would put that code in this delete method, in this dunder method. So if even one of the objects in the circular reference has a destructor, then the order of the destructors might be important, right? The order in which you destroy your object might be important. Maybe you cannot close the database connection until some other class that you have that was dependent or that was in the circular reference maybe deletes or commits a transaction or rolls back a transaction. Who knows, right? There could be steps or a certain order in which those steps have to be taken. So the garbage collector doesn't know what that order should be, and it would basically mark those objects as uncollectible. It would say, you know what, I don't know how to handle this, I'm not going to do it. And so when you had that situation with a circular reference where at least one of the objects had a destructor, then they weren't getting cleaned up, not by the garbage collector, and of course not by reference counting, and we would end up with a memory leak. Now that is no longer the case with version 3.4 and up. That particular problem has been resolved. So I really suggest that you do not use Python less than 3.4, right? Use Python 3.4 and above. All right, so let's take a look at some code and just put the garbage collector module through its paces and see what happens with circular references. So the first thing we're going to do is we're going to import the C-types library. Recall from the last video we're going to use that to look at the reference count given a memory address. We're also going to need to import GC, which is the garbage collection module. Okay, and we're going to bring back that same method that we had before to find the reference count for an object at a given memory address. And just return ctypes.clong.from address.value. Okay, so just what we had before. Nothing new here. Now, what is new is we're going to look at a method that's going to dig into the garbage collector, and it will tell us whether that object exists in the garbage collector or not. And we'll do that again by memory address. So we're going to define a new method. Let's call it object by ID. And we'll pass in the object ID or the memory address. And we're going to loop through every object in the garbage collector, and we're going to call the object getObjects method of the GC. That will basically look at every object that's inside the garbage collector. There's a lot of objects that get generated, and that's going to be the easiest way for us to find the object we're interested in. And we'll say if ID of object equals the ID that we passed in, right? So we're just going to compare memory addresses. We're going to say return object exists, right? And if we exhaust the loop, then we'll return not found. Okay. So this method is basically going to look at all the objects that are tracked by the garbage collector, and it will try and find the object that we're interested in by comparing the IDs. Okay. Now, there's another way that we can compare memory addresses, and we'll get to that in some future lesson. All right, so now comes time to create those two classes that are going to create a circular reference. So let's go ahead and create class A. Now, if you don't know object-oriented programming in Python, don't worry about it. These are pretty straightforward. And as I said, we'll dig into object-oriented programming in a lot more detail in a future section. So we're going to create a constructor, and that constructor is basically going to call another class that we haven't created yet. And what it's going to do, it's going to set its B variable equal to an instance of the class B, passing self. Now, self in this context means A, right? Means this instance of A. So we're going to pass the instance of A to B. And in B's constructor, we'll store that reference. So right now we're setting up that circular reference in exactly the same way we had in that diagram just a little while ago. So we have that, and then we're going to print some stuff out. Let's go ahead and print A. We'll print out what self is, and then we'll print out what B is. And by print it out, we're going to print out the memory address. So dot format. So what are we going to print out for A self? So we're in the A instance. The self, which is going to be the instance of A, is going to be hex of ID of self, right? And for B, we're going to print hex of ID of self.b. Okay? So basically, when the class instantiates itself, we're going to print out the memory addresses of the references. We're going to print out the memory address of our self, the instance of A, and we're also going to print out the memory address of the B instance that we created in this line here in the constructor. Okay, so that's class A. Now we need to do class B. And class B, again, we're going to declare an initializer. And here, we're going to say self. Now the initializer takes in an extra parameter. Let's call it A, right? That is what's being passed when B calls gets called, gets constructed. We pass in this reference to A. So that's going to come in here. So be careful. The self here and the self there don't mean the same thing. Self refers to the instance of this class B. Self here refers, and this self refers to the instance of class A in the code. So here we're going to set self.a equals A, right? So we're going to store the reference to A. And we're going to print out something very similar. So I'm going to copy paste. But now, of course, we're in class B, and we are going to print out ourselves. But now we're not going to print out B, we're going to print out A. That's the internal variable A. And so we're going to return the memory address of A. Okay? So now we've set up those two classes, A and B, with a circular reference. The next step, we are going to disable the garbage collector so we can see what's going on, because if we don't disable it, then as references go away, it's going to clean up the circular reference, but I don't want to clean it up now because we really want to take a look at what's going on. So we're going to disable the garbage collector. And now let's go ahead and create my var. Now my var is just an instance of A, and the initializer for A doesn't take any variable, any parameter. Okay, so as you can see, both the constructor for B ran, this is what it printed out. Okay, it said its reference was this number here, and then the reference for A was that 182F16 whatever. And you can see the constructor for A ran also. Now you can see that the memory address of A here is the same as the memory address of A here, right? This one is the A object self, right? And this is the B's .A memory address, right? This is the circular reference. And then these two are also equal to each other. Again, this is the reference that A holds to B, right? This is the memory address of the instance of B, and it's the same memory address here. Now, in fact, we can look at the ID of my var. Now, what do you think that should be? I'll let you think about it for a few seconds. My var is pointing to A. So the memory reference of my var should be exactly what A is, which is this one right here. Okay, so that matches. So that's good, right? So far, so good. Okay. So now, I mean, there's another way you can look at it as well, right? We can look at print, let's say, my var dot B. And my var, remember, B is an instance property of the class A. So my var, which is an instance of A, has this property B, and we can call hex of ID of my var B. We can also print, now we're going to print my var dot B. Now my var dot B is an instance of class B, and it has a property called A. So we can say dot A. And again, we're going to print the memory address of that as well. So if we print that, you'll notice that B, this should be the memory address for B, right? Which is exactly this one here. And this is the memory address from A, which is this one right here. And you can see that we recovered the memory address from A by looking at the object instance of B. Okay, so we have that circular reference. All right, so now let's take a look at a few things. Let's go ahead and print. Let's print the reference count. So I'm just going to print it like this, ref count. Remember that method that we created, right? Actually, before I do that, I need to hold references to A and B. So A.id equals ID of A, and B ID is equal to the ID of B. I don't need to store the ID of my var because it happens to be the same as the ID of A, since they're both pointing to the same object. And what did I do here? Oh, ID of A is my var. Sorry, right? We don't have a variable A. And the ID of B is simply my var.b. Okay, that's a little bit better. And again, we can check that just to be absolutely sure. Okay, we should probably, I'm storing the decimal because that's what we need to pass to those two functions, but I'll print out the hex version. Okay, as you can see again, A is this reference here, and B, well, my var.b is this reference dot here. Okay, and you'll see why I'm storing those memory addresses. We're going to need to have the stored memory addresses once those objects go away. We won't be able to access them by using my var because we're going to get rid of my var, right? So we're going to need to store those addresses. All right, so let's take a look at the, we're going to call our method refCount of AID. Now what should that be? Well, there should really be two, right? Because my var is pointing to A and B is pointing to A. And that's indeed what we get. Now what about the refCount for the B object? Well, the refCount is 1, right? Because only A is pointing to B. So that all seems to work out. Now we're also going to use that new method that we defined. Remember this one up here, object by ID. We're going to look in the garbage collector to see, is that object there? So we're going to say object by ID, and we're going to pass in the ID of A. And the object exists, right? Yeah, okay, cool. That's what we expected. And let's do the same thing for B. And the object exists. All right, good. So we have those references. We see what the reference count is, okay? So now let's go ahead and set my var equal to none. So basically, I'm destroying that reference between my var and A object, okay? So now let's look at the reference count of A. And the reference count is 1. And then the reference count of B is also 1. So as you can see, we got rid of my var, but there's still pointers to A and B because that's a circular reference. A is pointing to B and B is pointing back to A. And reference counting, therefore, is not going to help us out here because the reference count is non-zero. That's where the garbage collector comes in. Now, we can check still, make sure that those objects are indeed still being tracked by the garbage collector. You can see the object still exists. And we'll do the same thing with B. And we can see the object still exists. So those objects definitely are around. They have a reference count and the garbage collector is tracking them. But it hasn't cleaned them up. Why? Because we stopped the garbage collector, remember? Okay, so not something that you necessarily want to do. So now we're going to run the garbage collector manually. And we're going to say gc.collect. And that's how you can run the garbage collector manually. So now we've ran the garbage collector. And we're going to look at the object by ID of A underscore ID. It's not found, it's gone, right? And let's take a look at object by ID of B underscore ID. And it's not found. It's no longer in memory. So let's take a look at the reference count of A underscore ID. Oops. What's the method called? Ref underscore count. One. Now that's kind of weird, right? We should have destroyed that object. What about the reference count for B? That's weird. Let's try that again. Whoa. 1, 2, 5, 4. Now we have that many references to that memory address, but it should be 0. Well, what about A? Well, that's changed. Now it's some other big number. Now the odds are that when you run this code yourself, you'll get different numbers and you'll see them fluctuating, possibly. So what's going on? You want to think about that a little bit? What is going on? Why? We're not seeing the objects, right? If we try object by ID in the garbage collector, it tells us it's not in there. But I'm getting a reference count for that object, a.id. And it seems to change over time. If we do it again, who knows what we're going to get? Well, we get the same number. But it's definitely not 0. Well, this is why we usually don't use memory addresses and we don't work with memory addresses in Python unless you're trying to debug stuff or you're trying to do your own memory cleanup. You've got to be really careful using memory addresses. What is at that memory address right now? Remember the memory address that we stored for A, right? It was up here somewhere. Okay, a.id, right, was this value here, right? We stored it in a.id. What's in there right now? Yeah, we don't know. It could be something else. It could be nothing. Who knows? But that object is no longer A, right? It's no longer what this variable here was. It's no longer this instance of A. It's something else. And so trying to get the reference count of a memory address that is no longer necessarily managed by Python even, or even if it is, it's been reclaimed. Remember, the space, the memory address that was used by that variable was reclaimed. It's now being used for something else. Yeah, pretty obviously, right? And so who knows what that means? So you got to be very careful using memory addresses. It's okay to do this in this context. It's okay when you're trying to debug stuff. And it's okay if you understand what you're doing. And as long as you're using a memory address for an object that you know exists and you know what it is. But once the garbage collector ran, it destroyed all the objects involved in that circular reference. And those memory addresses we had stored are no longer applicable. Okay, so you really have to be careful with that. All right, thanks for watching, and I'll see you in the next video. Hi, and welcome to this lecture on dynamic typing versus static typing. Now, in order to understand this, I'm going to start by looking at what static typing is. So many languages are statically typed. Languages like Java, C++, C#, Swift, and many others are statically typed. So let's look at Java as an example. In this piece of code there, we have string myvar equals hello. Now there's a few things happening here. One is that we have a variable name, just like we have in Python. That's no different. What is different though is that we have a data type that we're associating with the variable name. This data type is a string. And then lastly, we have a value, a string literal, hello, that we're assigning to myvar. So now what's happening is very similar to what happens with Python. That string literal hello gets created in memory as an object at some memory address. It has a data type of string, it has a value, hello, and the memory address. What's a little bit different is that myvar is a variable, but it is a variable of type string. We have associated the data type with the variable. And then that variable becomes a reference to that memory address, just like we have in Python. So that's really the crux of the difference between Python and a statically typed language like Java. The data type is associated with the variable name. So if we write some code later on like myvar equals 10, well, this isn't going to work. It's not going to work because myvar was declared as a string, and 10 is an integer. It's not a type that is compatible with string. So that won't work. We can, however, say later on in our code, myvar equals ABC, right? The string literal ABC, that's perfectly fine because, well, ABC is a string. So that's okay, right? So that's really the main difference. Now Python is dynamically typed. So the main difference, if we look at this piece of Python code here, is that we're not specifying that myvar is of type string. Myvar is just a reference, nothing more, to an object. That object currently happens to be a string object with a value of hello. But the type is not attached to myvar. So just like we've seen before, myvar is a reference to the string object in memory. Later on, if we say myvar equals 10, that's perfectly legal. All we're doing is that we are creating an object in memory, an integer object with value 10, and we are changing the reference of myvar to point to that integer. So in effect, we kind of think that the type of myvar has changed. Well, myvar never had a type to start off with. Myvar was just a reference. What has changed is the type of the object that myvar was pointing to, right? So we can use the built-in type function to determine the type of the object currently referenced by a variable, but that can change over time. Remember, Python types, the variables do not have an inherent static type. So when we call type of myvar, Python will look up the object that myvar is referencing currently, right, that it's pointing to, and it will return the type of that object. So let's take a look at some code and see how that works. All right, so let's take a look at this very quickly. Let's start with a variable a, and let's make it equal to a string. So remember, a now is a reference to a string object in memory, has a memory address and so on. Now we can look at the type of a and we get that it's a string. Now, it's not really the type of a. Keep that in mind. What it really is, it's the type of the object that a is referencing. So if later we change a's reference to something else, maybe we change it to an integer. Now we can look at the type of a and we see that the type is now an integer. Maybe we change it to something else. Maybe, and this is something we'll cover later, we'll change it to, let's say, a lambda expression, right? So basically it's a function. A is a function, right? We can call a with a value of 2. It's going to return 2 squared because x is the parameter. It has a value of 2. So we get 4. And we can look at the type of a, and a is a function, right? If a is equal to 3 plus 4j, which is now a complex number, we can look at the type of a, and it tells us that it's a complex number, and so on. Every time we've simply changed the reference of a to a different object, and type will return the type of that object in memory. So quite straightforward, and that's what a dynamically typed language is. All right, I'll see you in the next video. Hi. In this video, I just want to talk very quickly about variable reassignment. Now, we've already seen this before, but I want to emphasize a certain point. So suppose we have this line of code, myvar equals 10. Now, we know already what's happening, right? We have an object in memory that gets created at some memory address, type integer, value 10, and myvar is simply a reference to that object, a pointer. If we later write a line of code like myvar equals 15, then we are not changing the value inside that object. That's the point that I want to make in this video. Instead, what's happening is that a new object, also of type integer, but with a value of 15, is created at some different memory address. And the reference of myvar changes to this new object. So myvar now points to this new object, but we have not changed the value of this object at memory address, let's say 1000. Okay? Instead, we created a new object at a different memory address. So that's a really important point that I want to stress that. And in fact, even if you look, let's say, at this code, so let's start again, myvar equals 10, myvar is a pointer to that object. If we write myvar equals myvar plus 5, the same thing happens. Don't be fooled. Don't think that because we have myvar on both sides of this expression that somehow something changes and now we're changing the value of that object. We are not. Python first evaluates the right-hand side. So it looks at my var, says, hey, I have to add 5 to my var. Okay, what's my var? My var is an integer with a value of 10. Okay, that's integer addition. 10 plus 5 is 15. It creates a new object in memory, okay, at a different memory address with a value of 15, and my var now points to that new object. But we did not change the contents or the value or the state of the object at address 1000. In fact, the content of integers can never be changed. And we'll look at that in the next section when we look at mutability and immutability of objects. So that will be coming right up, but first let's take a look at some code and just see this in action very quickly. Okay, so let's just look at this in some code. So we create this variable a, we assign it the value of 10. So it created an object in memory of type integer at some memory address. We can look at the memory address, that's the memory address. We can even, if we want, look at the type of a, which is integer. So let's now say a equals 15. Okay, now we can again look at the memory address of a, and you'll notice that the memory address of a has changed. It was, ending in AF0, and here we see it ends in B90. Different object. So that's what happened when we changed the value of a. We actually just reassigned the reference of a to a different object. And it's no different if we say a equals a plus 1, then we'll get something similar. We'll see that the memory address now of a has changed yet again. Right? Now a is a value of 16, and it's a different object in memory, EBB0 in this case. Now, before we finish up, I want to show you something that might surprise you. Let's say we have a equals 10 again, and let's create another variable, b equals 10. And let's look at the memory address of a, and let's look at the memory address of b. You'll notice the memory address of a and b are the same. In other words, a and b are both pointing to the same object. They're both pointing to an object at that memory address that happens to be an integer with a value of 10. So we'll look at that in the next video. We'll consider mutability and immutability. And we'll see then after that why it's actually safe for that to happen. And then in a future video, probably 4 or 5 videos from here, we'll look at why this is happening. Why is Python doing this? Why is it reusing that memory address essentially? Okay, so but first we're going to look at mutability and immutability, and then we'll see why it's actually safe for Python to do something like that, and then we'll look at why it actually does it. All right, I'll see you in the next video. Hi, and welcome to this lesson on object mutability and immutability. So let's consider again an object in memory. So remember, an object is basically something that has a type, and it also has some internal data. It has state, and it's located at some memory address. So changing the data inside the object is called modifying the internal state of the object. So let's take a look at an example of that. Let's say we have this variable myAccount, and myAccount references some object in memory at some memory address. Let's say memory address 1000. And let's say that the data type of this object is bank account, and bank account has 2 instance properties. It has an account number and a balance. So right now the account number is 12345, the balance is 150. Now suppose that we modify the balance. So we've changed the balance, we've deposited some money, and now the balance is 500. So you'll notice that the internal state, the data, has changed, but the memory address has not changed, right? So unlike when we were dealing with integers where we had, my var was pointing to 10, and then when we said my var equals 15, it changed the reference to a new integer object containing 15. Here, we're actually modifying the internal state of the same object. All right, so the data has changed, but the memory address has not changed. And we say that the object was mutated, which is really just a fancy way of saying that the internal state of the object changed. Okay, so there's a little bit of a difference. So now we can get to a definition. An object whose internal state can be changed is called mutable. But an object whose internal state cannot be changed is called immutable. Right? So these are just two definitions that you should remember and keep in mind, because that is important as we create objects throughout the lifetime of our programs. We kind of need to know, are those mutable objects or those immutable objects? It can make a difference. So let's look at some examples in Python, and let's start with immutable objects. Well, all numbers in Python are immutable. So ints, floats, booleans, complex numbers, these are all immutable objects. In other words, they get created in memory at some memory address, but we can never change the internal data, the internal value of that number. And we saw that in the last lesson when we were creating myvar equals 10 and then we said myvar equals 15. We saw that we were actually changing the reference from one integer 10 to another integer with a value of 15. We never modified the internal state that was contained inside that integer. And that's in part because integers are immutable. Strings are also immutable. Once you create a string, you can never modify that string. You can assign a new string to your variable, but you cannot change the internal state of that string. Tuples are also immutable, and we'll look at that in a few seconds. But tuples, if you remember, are created with round brackets. They're essentially a container type of object that contains elements. Now, the tuple is immutable in the sense that you cannot add or remove or replace elements in that list or in that container. Frozen sets, which we'll look at in a lot more detail in this course, are also immutable type of objects. And of course, user-defined classes can also be immutable. If you define your own class and you don't allow for any way of modifying the internal state of that object, you've created an immutable object. Now, what about mutable types? Well, lists in Python are mutable. Lists, if you remember, are created with square brackets, and they're also a container type, just like a tuple is a container type. The difference between the list and the tuple is that in lists, you can add, remove, or replace elements in that list. So the list is a mutable object. Sets are also mutable, and we'll again look into sets in a lot of detail in this course. But sets are mutable, as are dictionaries, and sets and dictionaries are actually very related. But dictionaries are also mutable. You can add keys, you can remove keys, you can modify the value assigned to a key inside a dictionary, and so on. And again, we'll look into dictionaries in a lot of detail in this course. And of course, your own user-defined classes can be mutable. You can write a class and you can allow people to change the value of, variables inside your class. You can allow state changes to happen, in which case you have a mutable object. All right, but a word of warning about mutability and immutability. And it's a fine point, but let's take a look at a tuple. So let's say t equals 1, 2, 3. So this is a tuple. Now remember, the tuple is immutable, right? So you cannot add or remove or replace elements in that list. Now furthermore, in this case, the tuple itself is immutable, but all the elements inside the tuple are integers, and so they are also immutable. But now consider this. Let's say that we create two variables, a and b, both lists. Now, lists we know are mutable. We can add elements, remove elements, replace elements in lists. So those are a mutable type of objects. Now, let's create a tuple that consists of two elements, a and b. In other words, t is a tuple where the first element is a list containing 1 and 2, and the second element is also a list containing 3 and 4. Now, we've got to be a little careful here, because we can now add elements to A and B, because A and B are lists and are mutable. So now, once we've executed those 2 lines of code, our tuple looks like this, right? The first element changed from 1, 2 to 1, 2, 3, and the second element changed from 3, 4 to 3, 4, 5. So you'll notice that, yes, the tuple is immutable. We did not change the elements that are referenced in these 2 positions, right? This 1, 2 and 1, 2, 3 are still the same object reference. They're still the same memory address. Same thing with the second element. We cannot add elements to T. We cannot remove an element from it. And we cannot replace an element with a new object, a new memory address reference. But we can certainly change the state of the object that's referenced in both positions of T. So yes, T is immutable, but the elements that T contained were not immutable. So in fact, T changed. From our perspective, the values that T contained changed. But T is immutable. Well, this is why we've got to be careful about what immutability really means, right? The tuple is immutable, but it can contain mutable elements. So do not confuse mutability with something that's completely frozen, that can never change, that it's not absolutely fixed. It can sometimes change. In the first example that we had, where we contained 3 integers, yes, that was completely, frozen. It could never change, because not only was the tuple immutable, but it contained only immutable integers. Okay. So we just have to be careful here. So let's look at this. T equals 1, 2, 3. The tuple is immutable. So these are references to immutable objects, right, of type integer. So this will never change. However, in the second case that we looked at, tuple equals the list 1, 2, 3, 4. The tuple is still immutable. That hasn't changed. But those are references to mutable objects. And so we can change them. Right? So a very subtle point, but one to be careful with. So let's take a look at some code. Let's jump into some code and see all this in action and just make sure we understand it. Let's start with a list. So let's say we have my list equals 1, 2, 3. Okay? So this is a memory address. My list is an object. It's a list object, so we can actually do type of my list. It will tell us it's a list. We can also look at the memory address of my list, which is that. Now we can append an element to my list. We could do something like this, append 4. So now if we print my list out, we have 1, 2, 3, 4, but we'll notice that the ID, the memory address of my list, has not changed. This memory address here is the same that it was back there, right? So it hasn't changed. Now, let me show you a different way of putting elements into the list. Let's say we have my list 1 is equal to 1, 2, 3, right? So it's that it has an address, my list 1. Okay, so this address here, which you'll notice is not the same as my list. Even though they contain the same values, they're not the same objects. Now I could do this. I could say my list underscore 1 is equal to my list underscore 1 plus, and I'm going to add that element, which is another list with one element 4. Okay. Now we can look at what it is. It's now 1, 2, 3, 4. But you notice we didn't append here. What we did is we concatenated 2 objects. So what Python does, it first evaluates the right-hand side. So it first evaluated my list 1 plus list 4. And then it combined those 2 lists and returned a new object. And in fact, if we look at my list 1, we'll notice that its memory address is not the same as it used to be. That was changed. This was not modifying the internal state of my list 1, right? The .append method was modifying the internal state. So we'll get to those methods when we look at lists in detail, but for now, just be aware of that. Now, this is not just, the immutable objects is not just lists. We can say my dict equals, let's say we do a new dictionary. Now, you can create new dictionaries in a few ways. You can use the object constructor this way, or you can use a literal using these curly braces. I'm going to use dict. I like the keyword approach. So let's say key 1 equals 1, key 2 equals a. So now if we print out my dict, we'll see it contains these two key value pairs. Now we can look at the ID of my dict. Okay, so it's got this memory address. Now if we want to add another key in there, we can go and say key 3 equals, let's make it a floating point number. Okay, so now my dict is that. It's got these 3 keys, and the ID of my dict has not changed, right? It is still the same memory address. Okay, so now I want to take a look at that example that I showed you with tuples. So let's start with a tuple, 1, 2, 3. Okay. Now the ID of the tuple is something. It's again an object in memory, and every element of that collection, 1, 2, 3 in this case, are integers, and therefore they're also objects, and they happen to be immutable objects. So for example, I can look at the first element of the tuple. It gives us 1. I can look at the ID of the first element of the tuple, and this is where 1 is stored in memory. Okay, we can look at the ID of t and the second element in the tuple, and we get a different memory address, and so forth. So now let's go ahead and create a tuple that contains lists. So I'll just use literals. So let's say that the first element is 1, 2, and the second element is 3, 4. Okay? So now we can look at the ID of t. Okay? It has this memory address. Now we cannot add elements to the tuple. We can't remove elements, but we can certainly access the elements of the tuple, right? The first element is 1, 2. The second element is 3, 4. So we could take the first element and append, let's say 3. So now if we look at the tuple t, you'll notice that the first element has changed. Even though the tuple itself is immutable, the collection is immutable, the element was mutable. So we can modify the element itself. That's okay, but not the tuple. Okay? So that's really what I wanted to point out. It's a subtle distinction, but it's important to understand that just because you're dealing with an immutable object doesn't mean that the contents can't change, especially when it comes to collections. All right, so thanks for watching. I'll see you in the next video. Hi, and welcome to this video on function arguments and mutability. In particular, we're going to look at how our variables may or may not be affected by functions when we call them and pass our variables to them. And mutability and immutability is really important in that context. So just as an example and as a refresher from the last video, remember that strings, for example, in Python are immutable objects. So once a string has been created, the object can never be changed. So if we have this code, my var equals hello, the only way to change my var is to point it to a different object in memory. So for example, let's say my var points to some object at memory address 1000 that happens to be the string hello. The only way for my var to get a different value is for us to point my var to a different object in memory. We can never modify the contents of the object at that memory address 1000 because it's a string and strings are immutable. Okay? So let's take a look at then why immutable objects are generally safe from unintended side effects. And by side effects, I mean that if we call a function with our variable, then that function may or may not alter the value of our variable. If we have immutable objects, we have a general amount of safety. So let's take a look at that. Let's say we have this function here called process, and it takes in a parameter s, and it's going to modify that parameter by concatenating world onto it. So let's say in our main code now we define a variable, myvar, and set it equal to this literal string hello. So we have scopes, right? We have basically two scopes in this example. We have the scope of our module, and then we also have a scope that's the scope of this process function. So when we run myvar equals hello, then the module scope has a variable called myvar, and it points to some object in memory. This object right here at memory address 1000, let's say. When we run this piece of code, process myvar, we are calling the process function, the process method, and we are passing myvar as the argument, which means that myvar's reference, and this is really important, the reference is passed to process. Okay, so myvar's reference, 1000 in this case, is passed into process, and the process scope now stores that reference in the variable s. So s points to the same object in memory, right? Now, when we run this piece of code here, s equals s plus world, we are not going to be modifying the contents of this object because it's a string, it's immutable. So the only way that s can now be equal to hello world is for us to create a new object in memory, hello world, at some different memory address, and then the reference of s is going to change. S is no longer going to point to hello, it's going to point to this new object, hello world. So you'll notice that in the module scope, myvar's reference hasn't changed. It's still pointing to hello. In the process scope, s has now changed its pointer from hello to hello world. So now in our main module, when we print myvar, well, what is myvar? Myvar is still this reference over here. And so when we print myvar, we actually print out hello. So as you can see, because the string is immutable, we have safety in that we pass the string to a function, and that function can never change the value of that string. So that's what I mean by saying that immutable objects are safe from unintended side effects. But of course, if you remember our discussion from the last video, we've got to be a little careful with that, especially with like container style objects, like a tuple, for example. Even though tuples are immutable, their elements may be mutable. So we'll get to that in a minute. But let's first take a look at what happens when we have a mutable variable and why we don't have safety in that scenario. So let's say that we have this function now, process, which takes in a list, and it's going to append a value to that list. And let's say in our module code, we have mylist equals this list 1, 2, 3. So again, let's look at the scopes. We have module scope and process scope. So mylist points to some object in memory, which is a list at some memory address 1000. Now when we call process passing in mylist, we're essentially again passing the reference to mylist, right, to the process method. So mylist's reference, 1000 in this case, gets passed to process. Now, LST, therefore, which is the local variable here to process in the process scope, points to the same object, just like we had with the string before. Nothing has changed so far. Everything is the same. But now what happens when we run this line right here inside the process method? We append 100. But what object are we appending 100 to? Well, the object that we're currently pointing to, that LST currently points to, which is this one over here. And therefore, when we run that line of code, our list has changed, right? It has mutated. The contents of the list has changed. The memory address has not changed. It's still the same object. We've just changed its state. So now when we print my list, well, my list is still referencing that object here. So when we print that out, you'll notice that the list is now 1, 2, 3, 100. In other words, before we called the function, my list was 1, 2, 3. After the function has finished running, our list was modified by the function. So that's what I mean by a side effect, right? That process method actually changed the state of our variable. Okay? So mutable objects are not safe from unintended side effects. So whenever you can use immutable objects, it's safer to do so. Now let's just take a look at that tuple example that we had in the last video, which is an immutable collection object, right? Tuples, you cannot add, remove, or replace elements in a tuple, but the elements themselves can be mutable. So let's take a look at this function again. Our process function is going to take in a tuple, and I'm assuming here that the first element of the tuple is going to be a list. So we're going to grab the first element of t and we're going to append 3 to it. Now in our main module code, we have this tuple here, which has 2 elements. The first one is a list, the second one is a string. String is immutable, the list, however, is not. It is a mutable object. So again, we have scopes. So in our module scope, we have my tuple, which points to some object in memory, which has 2 elements. First one is that list, second one is that string. When we call process my tuple, well, my tuple's reference is being passed to process. So now the process scope has this variable t that points to the same object. When we run this line of code, t0 append 3, we've just modified the object over here. We've added 3 to that list, right, which is the first element inside the tuple. You'll notice that the memory address of the tuple stayed the same. That hasn't changed. What has changed is the contents of the first element, because it was a mutable object. So now when we print my tuple, well, my tuple is still referencing that object. It has changed, right? So it is now 1, 2, 3, comma a. So very similar to what we saw in the previous video. All right, so let's take a look at some code and let's just see how this works in practice. So let's create a method that's going to modify its argument. So we'll start with a string. So we'll start by examining immutable objects. So let's write this method that we saw before, def process. Now what I'm going to do in this method is actually print out the memory address of the variables as we go along. So here I'm going to print the initial s memory address equals that, and we'll pass in, we'll just do the ID of s. Okay, so we'll stick with the decimal version, the base 10 version. And now we're going to modify s by concatenating whatever s was with, let's say, world. And I'm going to print again what that value is for s. So let's call that final s. Okay, so that's our function. It's basically going to modify s, and we're going to print the memory address of s before we modify it and after we modify it. So remember, we should see 2 different memory addresses because s is a string, it's immutable. So therefore, the only way to modify s is to point it to a different object. So let's say we have my var equals hello. Okay, and we're going to print the memory address of hello. So we're going to say my var memory address. I'll use a pound sign to indicate a memory address. And we'll print the ID of my var. Okay? So as you can see, that's the memory address of my var. Now we can call process of my var. Okay? And you'll notice that the initial memory address that was received here is the same So this memory address here is the same as my var. But you'll notice that after we've modified s, the memory address is different. And in fact, the ID of my var, if we check now, it is still the original memory address of my var, right? Which was this one here, and this one here. That hasn't changed, and therefore the value of my var hasn't changed either. It is still hello. Even though before process finished running, s was now hello world, but it was at a different memory address. Okay. So let's look now at the example where we have a mutable object. So let's call this one modify list, and we'll take in a list, let's say LST, and we're going to do the same thing here. I'm going to just copy and paste this code. Actually, I'll copy and paste everything, and I'll rename this LST. Now here, we're not concatenating. We're going to say lst.append. Let's append, let's say, the value 100. Okay, and then we'll modify this as well. Just fix up for the parameter name in the method. Okay, so now we have this method created that will modify the list. But notice I'm using this append, which means that we're going to be modifying the object state. Okay, so now if I have a variable called myList, let's say 1, 2, 3, okay, we can look at the ID of myList. So we can see the ID of myList is some number here. When we call modify list and pass in myList, pass in that reference to myList, then you can see that initially, right, what was received in modify list, this memory address, is the same as myList. And after we finished appending, you'll notice that the memory address of that list is still the same. So no memory address references have changed. They stayed the same. And in fact, ID of myList is still the same, right? It ends in 2632, so we're still dealing with the same object. So throughout this entire set of code here, we were dealing with the same object. And if we print out myList, you'll notice that it was changed. So we didn't modify myList in our main code. We modified myList inside this function here. And because lists are mutable objects, it is possible to modify what we pass into a function from within the function because it's a shared reference. Remember shared references from a while back? Well, this is what's happening here. So mutable objects do not have the safety, right? Strings are safe, right? They're not going to be changed. Integers, same thing. Any numbers, right? Any mutable object is not safe, and any immutable object is safe to a certain degree. So let's take a look at the tuple example, right? So let's go ahead and say modify tuple. So we'll pass in a tuple t, and again I'm just going to take all this code here, and we'll print the memory address of t. Now tuples, you cannot modify tuples. There is no append method to tuples. But I'm going to assume that the first element of the tuple is a list. So I'm going to take the first element of t and append 100 to it, and then we'll print out the memory address of t again. Okay? So there we go. And now let's write my tuple equals 1, 2. So the first element of my tuple is a list, and let's say the next element is a string. Okay? So we have an ID on my tuple. Okay, that's the memory address. Now keep in mind, the tuple itself is immutable, but in this case, the first element of the tuple is mutable. So when we call modify tuple and pass in t, look what happens. The memory address of t, oh sorry, not t, let's delete that, modify tuple of my tuple. Okay, so The memory address of my tuple, which was received here as t, is the same as my tuple. And after we finished appending the value to the first element, the memory address stays the same. The tuple hasn't changed, right? The tuple's memory address is still the same. What has changed is the first element of the tuple. So if we print my tuple out, you'll notice that the first element now had 100 appended to that list. So again, this is why you have to be a little careful when you say that immutable elements cannot change. Yes, that is true. The immutable object, the tuple object, cannot change in the sense that you cannot modify the elements, the containment of elements in that tuple. In other words, you cannot add, remove, or replace elements in the tuple. But if the element in the tuple is mutable, then you can certainly change its value in place. And so, in effect, from a programmer's perspective, the tuple's value has changed, right? So be careful. Immutability does not necessarily mean that nothing can change. It can. All right, thanks for watching, and I'll see you in the next video. Hi, and welcome to this video on shared references and mutability. Now, this is something we've actually already seen before, but I just want to formalize the definition and just re-emphasize a few points about this. So the term shared reference is the concept of two variables referencing the same object in memory. In other words, pointing to the same object, having the same memory address. So for example, if we write a equals 10, then we can create a shared reference to this object in memory. So we have this object in memory at some memory address and a points to it. We can create another variable that points to the same memory address simply by writing b equals a. Just keep in mind, Python variables are memory references. So when we say b equals a, what we're actually saying is set the memory reference of b equal to the memory reference of a. That's what that assignment is doing. It's not copying values, it's copying memory address references. So b points to the same object in memory. Now the same thing really happens when we define, let's say, this code here. Let's say we've got a function, myfunc, which takes a parameter v. Now in our main code, suppose we write t equals 20, then t is a pointer to some object in memory. When we call myfunc t, we're passing the reference of t into this function. And so in its scope, it's going to have a variable v that will point to the same reference. We saw that in the last video. But that is another way of creating shared references. So shared references exist all the time in our code. We usually have functions and we pass arguments into them. So we end up with shared references. Now the following may surprise you. And again, we've seen that before. And we'll come back and take a look at exactly what's happening. But if we write a equals 10 and another line of code b equals 10, we might expect b to point to a different object in memory. It should be a different object. But in fact, what ends up happening is that b references the same object in memory. Python did that automatically for us. And the same thing, if we look at a string, s1 equals hello, s2 equals hello, well, we end up with both s1 and s2 pointing to the same string. Again, Python's memory manager decides to automatically reuse these memory references. Well, we'll take a look at that very soon to see why that's happening. But the question here I want to answer is it even safe? And well, the answer is yes, because these objects are immutable. So even though a and b and s1 and s2 are both shared references, if we modify s2 or we modify b, the only way to modify the value that those variables are pointing to is by changing their memory address reference. And so by doing so, we would leave a and s1 alone. So yes, it's actually quite safe to do that, and Python actually uses that in order to do a few optimizations that we'll talk about when we get to Python optimizations. Now, when working with mutable objects, you have to be a little more careful, right? So let's say we create a shared reference. So a is a pointer to this object in memory, 1, 2, 3, the list, that's some memory address. And we set B equal to A. Again, remember, this creates a shared reference. So B points to the same object as A. Now we have to be careful, because if we modify B, let's say we append 100 to B, well, we're going to append 100 to this object here. That happens to be the same one that A is pointing to. So once we've modified the state of that object, well, then A has essentially as a value, as a developer, we think of A as just a list, right? Then its value has changed as well. Why? Because it's pointing to the same object in memory. So with mutable objects, the Python memory manager will never create shared references, because that would not be safe to do. So if we write this, A equals 1, 2, 3 and B equals 1, 2, 3, then we are going to end up with two different objects in memory. So we'll have this list at some memory address, and B will point to a different list with a different memory address. The lists are equal, they're both 1, 2, 3, but they're not the same objects. Okay, so let's look at some code and let's just see in practice how this works. So let's start with setting up our own shared reference. So let's say we have A equals, and we'll use a string. Let's say hello. And then we'll set B equal to A. So now we can look at the ID of A. Maybe I'll use the hex version, hex of ID of A. So this memory address. And if we look at the memory address of B, we'll find that we're actually pointing to the same memory address, right? So we set up a shared reference by setting B equal to A. Now, we know that Python does that automatically for us. If we say A equals hello and B equals hello, then we can look at the memory address of A and we can look at the memory address of B, and again we see that they are the same. Now, we didn't set up the shared reference. The Python memory manager did that. We'll revisit this in a few videos to see why it's doing that and when does it actually do this. It doesn't do that all the time. But the question that we asked was, is this safe to do? And yes, of course, because if we want to change B and let's say make B equal to hello world, right? Then if we look at the ID of B now, it has changed, right? It used to be this memory address right here, and now it is this memory address. It has changed. But the memory address of A, well, we didn't touch that, right? That stayed the original memory address, okay? So A is still hello, and B now is hello world. And that's because a string is immutable, so the only way to change the value of B, right, the perceived value of B, is by pointing B to a different string object. Okay. Now, it's not quite the same when you're dealing with a mutable object. So let's use a list, which is a mutable object, and let's set a shared reference by setting B equal to A. Now, again, the memory address of A and the memory address of B are the same, right? As you can see, they're both the same memory address, which means, again, we have a shared reference. So if we say B append 100, then we're going to append 100 to that list, but it's a shared, it's a list that's shared between the variables A and B. Both A and B are pointing to the same list. So the memory addresses of A and B are still the same as before and still equal to each other, okay? And if we look at the contents of B, it's 1, 2, 3, 100, and A is going to be the same. So by modifying B, we modified A. And that, of course, also happens when you pass a list into a function, right? The function creates a shared reference to that list and can possibly modify your list outside, right? That you define outside of the function, but you passed into it. So you have to be careful when you're dealing with mutable objects, because everything in Python is passed by reference. And so you can get unintended side effects. You can also get intended side effects, is that if that's what your function wants to do. If you want to do an in-place sort maybe of the list, then this is great, right? Because you can do an in-place sort, you don't have to return it and reassign it. But you can also have unintended consequences. Okay, so lastly, one thing I want to look at very quickly is just this concept of this shared reference that Python does for us automatically, right? We looked at hex of ID of A, hex of ID of B had the same reference. Well, I just want to show you that if we do that with an integer, A equals 10, B equals 10, then we can look at the memory address of A, and we can look at the memory address of B. Okay, you can see that they're the same. So Python did this automatic shared reference for us. We'll revisit this, but one thing I want to point out here is that don't count on it. It doesn't always happen. Let's say we say A equals 500 and B equals 500. Then we can look at the memory address of A again, which is that, and the memory address of B, which is a different memory address, okay, 8910, 8A90. So it doesn't always do it, right? Sometimes it does, sometimes it doesn't. We'll find out very soon when it does and why it does so. All right, thanks for watching, and I'll see you in the next video. Hi, and welcome to this video on variable equality. So variable equality, we can think of how to compare two variables in two very fundamentally different ways. The first one is by comparing the memory address, right? As we know, variables are simply pointers to objects in memory, and so we may want to find out, are these two variables pointing to the same object? That's comparing the memory address. We may also want to just compare the internal state of the objects, the data. For example, the contents of two lists. They may not reside at the same memory address, but they may have the same content. And the same thing with strings and number values and all the different objects and data types that we can have in Python. So to compare memory addresses, we use a special operator called is, which is called the identity operator. So to compare two variables, you might say val1 is val2. That will return a Boolean true or false, telling you whether they have the same memory address or not. So remember how we were checking before the memory address, right, by doing ID of A and ID of B and comparing the two and seeing if they were equal? Well, you can do the same thing in code using the is operator, the identity operator, which compares memory addresses. On the other hand, if we want to compare the internal states of the objects, we use the equality operator, which is this double equal sign. Now, be careful, it is not a single equal sign. A single equal sign is an assignment operator. The double equal sign is the equality operator, which will compare the internal state, the data of the two variables. So you would say val1 equals val2. That will tell you whether the contents of val1 and val2 are equal. Now, if you want to test the opposite, if you want to test that the memory address of one variable isn't the same as the memory address of the other variable, then you can use the special operator is not. And that will, you can use it this way. Val1 is not val2, and it will tell you that it will again return a Boolean true or false that will tell you whether those two things are equal or not. Now, you don't have to use is not. If you want, you can just say not val1 is val2. That's one alternative way of checking. But preferably use is not. For the object state, we also have the negation of the equality operator, which is the exclamation point equals. So not equals. Remember that this exclamation point in a lot of different languages also means a Boolean not. Well, here we have not equals written this way, even though in Python the not operator is actually spelled out not, like we have here. And so you would say val1 not equals val2. Now again, there's different ways that you can write this. You could say not val1 equals val2. Okay, so let's look at some examples. So let's say we have A equals 10 and B equals A. So we've created a shared reference here. So let's look at how each of these will evaluate. A is B. Well, that's going to return true. It's a shared reference. It's got the same memory address. But A equals B will also return true because, well, both A and B are integers that contain the value 10. So in terms of values, they're equal. Let's say we look at two strings. Now, this is kind of a special case. If we look at A is B, if you remember the previous video, we mentioned that the Python memory manager is actually going to create a shared reference with this string. So A is B is actually going to return true in this case. But, as we'll see later, do not count on it. So this is why I'm saying in general, when you want to compare the values of two variables, you're generally going to always be using equals equals. It is rare that you're going to use is, because is comparing memory addresses. So A equals B will return true, and in this case only, A is B will also return true. But if this was a different string, A is B might not return true, so don't count on it. Now let's take a look at two mutable objects. We know that these will definitely be different memory addresses, right? These are mutable objects. So even though we've created them with the same values, Python isn't going to use a shared reference here. And so A is B will return false. However, the two lists are actually equal in terms of values, and so that will return true. And we'll look at equality of lists later, because it can actually nest deeper. You can have lists within lists, or dictionaries within lists, within dictionaries, and the equals equals will actually dig down into all those nested data types. So now let's look at this last one, which is a little bit different, because A equals 10 and B equals 10.0. So this first one, A, is an integer, but B is a float. So in this case, Python is not going to create a shared reference like we would have if A equals 10 and B equals 10. So A is B is going to be definitely false. And A equals B, even though it's not the same data type, right? A is of type integer and B is of type float. The two values are still actually equal. Python figures that out. It's a number, right? And numbers contain integers and floats and decimals, booleans and complex numbers and so on. And so we'll get the same value. So in terms of value, they're the same, right? 10 and 10.0 are actually the same. We'll revisit floats later because we've got to be a little careful with floats. We don't have exact representations of floats in memory. So in this case we did, and therefore the two values were the same. Lastly, I want to talk very quickly about the none object. Now the none object can be assigned to variables to indicate that they are not set, right, in the way that we would expect them to be. So for example, let's say that we have a variable that's supposed to be a string, but we don't have a value for it yet. So we may set it equal to none, right? In other languages like C, you may think of that as a null pointer, right? You can think of it as an empty value. But nonetheless, this none object is a real object that is managed by the Python memory manager. So the memory manager will always create a shared reference to none. So whenever you assign a variable to none, if you have any number of variables assigned to none, they will all have the same memory address. Again, that's just the Python manager doing that for us, right? It's not creating a new instance of none every time. It's just pointing to the same one all the time. So this means that if we set, let's say, A, B, and C to none, right, then A, B, and C are all pointing to the same object in memory. And throughout the lifetime of your application, it will always point to the same object, to the same memory address. Now, as you run your program from one time to another, that memory address may change, but throughout the lifetime of your application, it will be the same. So we can test if a variable is not set or empty by comparing its memory address to the memory address of none using the is operator. So we can test A is none, right? And so this is just something I wanted to point out now since we talked about the identity operator is, okay? So that will evaluate to true. Now just keep in mind, none is not nothing. It's not, it's not nothing. It is an actual object. But it is quite useful in terms of being able to set variables to none to indicate, hey, they don't have a value, right? They do. The value just happens to be none, but that's quite useful. And we'll see that throughout this course where we can use that to good effect. So if we have, let's say, x equals 10, if we say x is none, well, that's going to return false, right? Because x is not none. X is an actual value, an actual object, 10. And if we test x is not none, that will, however, return true, right? That's the negation of the identity operator. Let's start by looking at two variables that are going to have a shared reference. So we can say a equals 10 and b equals 10. Now we know that the Python Memory Manager is creating a shared reference automatically for us. We can check that by looking at ID of a and the ID of b, okay, which happens to have the same ID. So it's a shared reference, same memory address, and therefore same internal content, same value. So we can print, let's say a is b, and we'll print out the result of a is b. Well, in this case, it's true because they're pointing to the same memory address. And of course, in terms of a value, if we look at a equals b, we'll print out the result of a equals b. Well, we get true as well, which makes sense. They're both 10. Okay. Now let's do something that's not a shared reference. We've seen that in the past as well. We can create two variables. Let's say a and b, both 500. Now the ID of a is that, and the ID of b is something else, right? So now if we want to print, and I'm just going to copy paste, so we'll print a is b, and we get false because, well, they're not the same memory address. However, the values are still the same, right? So a equals b will be true. Okay. Now same thing, if we have a list, let's say a equals 1, 2, 3 and b equals 1, 2, 3. Well, we know that the ID of a and the ID of b are going to be different, right? As you can see, 168, 416. We've got different memory addresses here. And so the same is going to happen where a is b is going to be false, but a equals b is going to be true, right? Because the contents of the two lists are the same. They're equal. Okay. So the same thing also happens when you're looking at numbers. You can say, let's say a equals 10 and b equals 10.0, right? So again, let's print out this. Then we'll find that a is b is false. Yes, absolutely, because we know that this is an integer, this is a float. Can't be the same object, so they have to have a different memory address. But in terms of values, well, they are equal. 10 and 10.0 are the same number when we think of it logically, right? We can also look at, let's say we have a equals 10, b equals 10. We can even make a equal to 10 plus 0j. Now that's a complex number. If we look at the type of a, that is a complex number, right? And the type of b is a float. So again, here's the results of using memory address comparison, the equality operator, and the identity operator, right? Is and equals equals. But we can see that in terms of identity, a is not b, which is true, right? Because a is complex, b is a float. But in terms of value, 10 and the complex number 10 plus 0, j or 0i, if you'll use the I notation for complex numbers, are obviously the same value. All right? So next, let's look at the none object. I just want to talk about that. So let's first of all look at the none object, right? It has a memory address, right? Here's the ID of none. It has a type, right? It is an object that has the type none type, okay? So it's a real object in memory. The only thing is that if we have a equals none, b equals none, c equals none, then the ID of a, and instead of me printing out the ID and checking if it's equal to the ID of b, how about I just do a is b, right? That's what we use to check memory addresses. So a is b is true, and a is c. Well, that's true as well. And in fact, a is none is also true, and b is none, and c is none. Okay, all these are true. So it is helpful to use the none operator to just be able to create a variable but not assign a value to it yet, or maybe at some point in time to remove the value that a variable has and say that, hey, it doesn't have anything in it right now. I still want to keep the variable name around. For some reason, I'm going to put something in it later. But for now, I'm going to point it to this none object. And then we can test in our code to see if a variable is set to none. And then we can maybe have an if statement that says, okay, if it's none, do this, otherwise do that, right? So it might be something like trying to read a file, if the file contents exist, if the file exists, and the contents are there, set, A equal to the contents of the file. If the file doesn't exist, set A equal to none, right? And then later on, you can check to say, well, if A is none, which means, hey, the file wasn't there, do something, otherwise do something else. So none is used for scenarios like that. But none is an object, but it just happens to be really useful because Python's memory manager will create shared references to that none object. All right, thanks for watching, and I'll see you in the next video. Hi. In this video, we're going to look at objects in Python, and we're going to look at the statement that a lot of people make that everything is an object in Python. And that's really basically true. So in this course, we're going to encounter many data types. We're going to look at integers, booleans, floats, strings, lists, okay, all very typical objects, tuples, sets. We'll look at dictionaries, the none type that we've seen before. But we'll see other things as well, right? We're going to deal with operators like plus, minus, that equals, that equality operator, or the is, the identity operator, and so on. Even this operator here, which is an operator, it's an ellipsis. We're also going to look at functions, obviously, and classes, and types, right? All things that we've actually seen before and things that you've seen before in Python. And we're going to see many, many more throughout this course. So these are all different things, right? You have data types, you got operators, classes, functions, but there's one thing in common to all of those things, is that they are all objects. In other words, they are all instances of classes. So for example, the functions are instances of the function class, right? There is a class in Python that's named function, and when you create a function, it is an instance of that class. Same thing with classes, right? And I'm not talking about the instances of a class. Obviously, these are objects, they're instances of a class. But the class that you define yourself, when you, let's say, do a user-defined class, that is an object, right? The class itself is an instance of the class type. Same thing with types. The type itself. Remember when we typed type of int, right, or type of a variable a that was an int, and it told us int? Well, that is a class, right? There is a class called int. So this means that all of these things have memory addresses, right? In particular, functions have a memory address. And that's going to be really important throughout this course. So let's take a sidebar and look at that. Let's say we create this function, def myfunc, okay? So this is the name of the function, myfunc. And then maybe here we have some parameters. Well, what happens is that myfunc is basically our variable name, but our variable points to a function object, right, that exists at some memory address and has some state. Now, the state of the function includes many things. It includes, well, obviously the code, right, that's typed in myfunc, but also what's happening to variables as they get created within that scope and so on. So all of that is bound to the function state. So we can look at the ID of myfunc, just like we can call ID on any other variable. Well, myfunc is just another variable, just happens to be a function object instead of an integer object, right? So we can call that, and we will get back that memory address, whatever that is. Now, we are not going to be using the memory addresses of functions in our code, right? I just want to point this out so we understand what's happening. Now, what this means is that as a consequence, well, remember, any object can be assigned to a variable, well, including functions. You can assign a function to a variable, and we'll see some examples of that in a minute. Any object can be passed to a function, right? Passed into the arguments of the function, into the parameters as an argument. Well, that means that functions can also be passed to functions, something that we'll make a lot of use of when we're looking at things like decorators, for example. Now, any object can also be returned from a function, right, in the return statement, including, you guessed it, functions, right? So functions are first-class citizens, just like any other variable, like integer or float, would be. right? You can reference them, you can assign them to a variable, you can reference them however you want, which means you can pass them into functions, you can get them as a return from a function, right? And this really makes Python very powerful. Okay, so one little side note that I want to make, and that's in terms of this myfunc here. Okay, it's very important. Myfunc without the parentheses is the name of the function. If you use myfunc with the parentheses, that will invoke the function, right? So be very careful here. When we're going to pass around myfunc, we are not going to use the parentheses. We don't want to call the function. We don't want to invoke the function. We just want to pass the function name. Well, the function name is this name over here without the parentheses. Okay, when you have the parentheses and possibly even arguments there, you're actually calling or invoking the function. All right, so let's take a look at some code examples and see how all this works. So let's start by, let's say, creating a variable a, setting it equal to 10. Then we can print out the type of a, and it tells us that it's a class of type int. Right? So in other words, a is an int instance. So if a is an int instance, if int is a class, we should be able to create new instances of that class using our standard instantiation notation in Python for creating new objects given a class. So we could do this. We could say a equals int and then pass in the initial value for int. And you'll see that b, well, b is 10. And if we print the type of b, we get that it's an integer, right? So no different. It's just creating a new class, but this syntax allows us to not have to write this one. Now, sometimes we want to use this, and we'll see that when we start looking at integers in more detail. The other thing, too, is that classes in Python can have built-in documentation. And when we get to the object-oriented portion of this course, we'll see how to include documentation for our classes as we write them. But the built-in classes also have documentation, and you can bring them up by typing help, and then the class name that you're interested in. So help int, for example, will return a few things. It will tell us, okay, you have this kind of constructor, right, for int, where you can just pass in the value that you want to create as an integer. And by default, it will be equal to 0. So if you don't pass in a value, it will just create an integer with a value of 0. You can also create integers with different bases, right? So you can pass in, usually this will be a string, and you tell it what base you want it to be in, and it will convert it from that base. So let's take a look at that. Let's say we have c equals int, okay? Then c is 0. We can also say c equals int, and let's say I'm going to take in this string here, 101, and we'll do a base of 2. So base is a keyword argument, and we'll study what those are in an upcoming section with keyword arguments and parameters. So now if we look at the value of c, it's 5, right? Because this is the position 2 to the 2, which is 4. So we have 1, 4. We have 0, 2 to the 1s, and we have 1, 2 to the 0. So this is 5 in binary notation, which is base 2. So this is another way of creating integers. And so therefore integers are objects, right? And they're instance of the int class. Okay, so I really want to take a quick look now at the fact that functions are objects too. So let's go ahead and write this function here. We'll write a function called square, which is just going to return a squared, right? So a very simple function. You probably wouldn't want to write something like that in practice. Now let's look at the type of square, right? Square is the name of the function, so it's like a variable name, and it tells us that it is a function. Okay, in fact, you can print the type of square, and that will tell you it's a class of type function. Okay, so it is a function. So we can say f equals square, right? If square is a memory address reference, if it's a pointer, we can assign it to another variable. So we can do that, f equals square. And if we look at the ID of square, it has a memory address. And if we look at the ID of f, it has the same memory address, right? So f is square. That is true, right? So you can call square passing in 2, right? And it should return 4. But you can also call it by now invoking f, right? By using this parentheses. So if we do that, we get 4 as well, right? Now, a function can also return a function. So let's create another function here. Let's call it cube of a. And let's have it return a cubed, okay? And now I'm going to write another function. That's going to say def select function. And let's say we're going to pass in a function ID for now. I'm going to say if function ID equals 1, we're going to return square, else return cube, right? So what are we returning? Well, if we're going to pass in a value, if that value is 1, we're going to return the name. We're going to return this reference, right? That is referenced by this name, square. Otherwise, we're going to return this reference, cube. Okay? So now we can say f equals select function. And let's say we're going to select the square function. So we're going to do that. So now look at what the ID, well, of f and square is. F is square. That is true, right? Because why? Well, when we called select function with 1 as the argument, it received it here in function ID, and it said, oh, it's equal to 1, then return this function square. So we're passing functions around just like we would pass variables around. The only difference is that functions are invocable. So now we can say f of 2, which returns 4. If, on the other hand, we had said f equals select function 2, okay, then we'd see that f is actually cube, right? That is true. And f of 2 would return 8, right? So we can return functions from other functions, which is something that we're going to make really good use of. Now, you can also, if you want, if you don't want to have to assign it to a variable first, you can certainly do that. You can say select function, if I can type, select function. Let's say we'll select the cube function and we'll pass it the value of 3. Okay, that returns 27. What happened is that it first evaluated this, said, okay, I'm going to return, right, cube. And now it applied cubed, it invoked cube with 3 as the parameter. And we'll see that again in a lot of detail throughout this course. We'll be using that all the time. Now, a function can be passed to a function as well, right? So let's go ahead and write this method here, exec function. Again, probably not something you would write as is like this, but it does illustrate the point. So this function is going to take 2 parameters. The first parameter is going to be a function. And then we are going to apply this function to this variable here and return the value. So we're going to invoke fn, and its argument is going to be this parameter n. Okay? So now we could say exec function. Well, what do we want? Well, let's say we want to execute the cube function on the value 3. We get 27, right? So as you can see, we passed the reference to cube. It was assigned here. So now, by the way, remember there was a shared reference to that function. Okay. We also passed the value 3, and it received the function and the value, and it invoked the function fn, whatever it may be, right, with the value. So if we had done exec function square 3, we would get 9. All right, so functions are first-class citizens. They're objects, just like everything else in Python. So most everything is an object in Python, including operators, including types, including classes, functions, and what have you. All right, thanks for watching, and I'll see you in the next video. Hi, and welcome to this video on Python optimizations in turning. Python optimizations will cover in a few videos, and this one is going to focus on interning of integers in particular and what interning is. So one important note is that a lot of what we discussed with memory management and garbage collection and what we're going to discuss now with optimizations and memory footprints are really specific to the Python implementations you're using. Now, in this course, we're using CPython, which is kind of the standard, the reference Python implementation, which is written in C, hence the name CPython, but that's kind of the version of Python. However, there are many other versions of Python that exist. For example, Jython is written in Java, and it can import and use any Java classes. And in fact, it even compiles to Java bytecode, and so it then runs in a Java virtual machine. You also have IronPython. Now, IronPython is written in C#, and it targets the .NET CLR, or the Mono CLR. You also have PyPy. Now, that one's interesting. It's a Python interpreter written in Python. And it uses a specific version of Python. It doesn't use CPython. It uses RPython. RPython is a subset. It's a statically typed subset of Python that is written in C, but that is specifically built to build interpreters, in particular Python, for example. So that's PyPy. And there are many others. And if you're interested in that, you can take a look at that URL that's down here, that link, and you'll see that there are many other Python implementations as well. But for this course, and certainly for the purposes of these discussions, I'm referring to CPython. Now, the version of CPython also makes a difference. Okay. Now, in this version, in this course, I'm using version 3.6, and so depending on what you're using, your results may be slightly different. Okay, so earlier we saw that if we wrote that code, that Python code, a equals 10, b equals 10, then a was a reference, a pointer to some object in memory, integer, with value of 10. But b was also assigned the same memory address. So Python automatically created a shared reference for us. But look at this. If we write a equals 500 and b equals 500, then a points to this object in memory, but Python doesn't create a shared reference in this case. It points b to a new object at a different memory address. So it would be safe to create the shared reference because integers are immutable, but it doesn't. So what's going on? Well, it's something called interning, and interning basically is reusing objects on demand. So at startup, CPython preloads or caches a global list of integers in the range -5 to 256 inclusive. So what that means is that anytime we reference or use an integer in that range, Python is going to use the cached version of that object. It's not going to create a new one. It's going to look it up in its list and say, okay, I'm going to use this existing one already. So it's going to reuse that memory address. And that's what we saw. When we took an integer like 10 that was in that range, we saw that we were getting shared references. When we used 500, we saw that we were getting different references. That's because we're outside of that range. So essentially, the integers in the range -5 to 256 are singleton objects. And we'll get into exactly what singleton objects are when we get to the section on object-oriented programming. But basically, singleton objects are classes that can only be instantiated once. So whenever you try and reinstantiate them, you just get the original version back. So it's kind of the same thing that's happening here. Why do this? Well, it's an optimization strategy. Small integers show up relatively often in our code, and so Python decides, okay, I'm going to pre-cache a certain range of integers. You obviously don't want to pre-cache too many, right? Because now you're starting to incur memory overheads. This happens at startup, so startup may take too long if you try and cache too many, and there's a point of diminishing returns. But so they decided that -5 to 256 was a pretty good cross-section of interning. So now when we write a equals 10, well, Python just has to point to that existing reference for 10. It doesn't have to create that integer object. And creating an integer object does take some work. And we'll see also what the memory overhead is every time we create an integer. But if we write a equals 257, well, that's outside of the range, -5 to 256, then Python doesn't use the global list and we'll get a new object created every time. Okay, so let's take a look at some code and just see this in practice. So recall that Python will create singleton integer objects out of integers in the range -5 to 256. Okay, so that's the range. So if we create a equal to some number in that range, let's say 10, and then we also create b and make it equal to the same value, then remember what's going to happen is that the ID of a is going to be a certain memory address and the ID of b is going to be the same. So the Python memory manager basically will point you to that shared reference. Okay, so you have the same object being utilized. That's safe because integers are immutable. So we cannot change the value of b by modifying the contents of the reference, right, of the object being referenced, which means that a can never change because, well, we can never change the object that a points to. So the only way to change a is to change a's reference to something else. Okay, and changing that on b isn't going to affect what a is referencing. Just to show you that if we take a equal to -5 and we take b equal to -5, then the memory address, we can do it this way, are the same, right? Memory addresses are the same. Now the easiest way of comparing memory addresses, remember, is to use the identity operator is. So a is b, and it tells us, yes, it is. It is the same memory address. And if we take a equal to 256 and b equal to 256, then we can see if they have the same memory address, and they do. If we take a equal to 257 and b equal to 257, then a is b will return false, right? We are no longer using this singleton collection, right? So same thing, -6 and so on. Now, remember, we can create integers in different ways, right? We have a equal to 10, for example, right? We can also say b equals int 10. We can declare a new integer object using the constructor, okay? So we can pass in 10 that way. We can also say c is equal to int and pass in a string, okay? And that string, that constructor, will default to trying to create an integer base 10. Based on that string. If we want to try a different base, we could say int, and let's do 1010 in base 2, right? Which is actually 10 in base 10. Actually, let me go back and let's make that equal to d, right? So we have a, b, c, and d. So if we print a, actually we'll print a, comma b, comma c, comma d. Okay, they're all 10. And we can now print the ID of each one. ID of A, ID of B, ID of C, ID of D. That is because I'm sure the cell type changed to Markdown. So instead, let's run it as code. So there we go. All right, and as you can see, the memory address of each of these variables is the same. So it didn't matter how we created that, because the end result was an integer of value 10. It basically then looked it up and said, hey, I've got that already in my list of, interned integers. And there it is. I'll use that one. Okay, thanks for watching, and I'll see you in the next video. Hi, and welcome to this video that continues our series on Python optimizations. In particular, we're going to look at something called string interning. Now, we've seen interning before. We saw that in the last video, and we saw that Python automatically interns a certain range of integers. But some strings are also interned by Python, but not all. And that's really important to understand, that not all strings are interned. Now, as the Python code is compiled, identifiers are interned. Now, what are identifiers? They're things like variable names, function names, class names, and anything else that you use inside your code. Your code is essentially a lot of strings, right? And it gets compiled by Python, and it will in turn all these identifiers. Now, just as a reminder, identifiers must start with an underscore or a letter, and then they can only contain underscores, letters, and numbers. So some string literals also get automatically interned. Again, not all, but some. In general, any string that looks like an identifier will get interned. So the string hello world, well, that satisfies the rules for an identifier, and that will get interned. Now, even though it may start with a digit, so that technically it's not an identifier, those strings will still get interned as long as everything else looks like an identifier. But don't count on it, right? You shouldn't count on things getting interned. Python is interning those things for a reason. So why? Why is Python doing that? Well, it's all about optimization. And it's really about speed optimization and possibly memory optimization. If you think about what's happening as your Python code is running, Python needs to look up your identifiers, your variable names. If you reference a variable and you say print A, well, it needs to go and look up A. So it goes into a dictionary essentially and says, hey, where's A? Find A and tell me what it is, and then I can find the object and do whatever needs to happen with it. So there's a lot of string comparisons that have to occur, right? A lot of string equality testing. So let's look at two strings. Let's look at an example. Let's say we have some long string. Okay, so A equals some long string and B is the same value, some long string. Well, if we use A equals B, if we use equality comparison to compare the two strings, we have to do this character by character. However, if we know that some long string has been interned, then we know that A and B are both going to point to the same memory address. In that case, to check whether A and B are the same strings, we can actually just check whether they have the same memory address or not, right? And so we can use the identity operator, is, instead of the equality operator, the double equal sign. So we can compare memory addresses, which is just comparing two integer values for equality, instead of comparing two long strings character by character. And this is much faster than doing the character by character comparison. And in fact, we'll take a look at that in the code that we'll look at a little later in the video. So not all strings are interned by Python. You've got to be careful about that. But you can force strings to be interned yourself. So there is a method, the intern method in the sys module, that you can use to actually force interning of strings, basically making that particular string a singleton. So the way you would use it is you would first have to import the module, import sys, and then you would say A equals, and instead of just making it equal to the string, you would say sys.intern and then the string that you want. Now when you create B, you have to also do sys.intern. You can't just make it equal to the string itself, otherwise that will be a new object in memory. So in this case, A is B will evaluate to true, and it's a much faster comparison than doing A equals B. So when should you do this? Well, in general, don't do it, right? Unless you have a specific need. Now, when does that happen? Well, for example, let's say you're dealing with a very large corpus of data, right? A large number of strings that maybe has a high repetition. Maybe it's you're trying to tokenize, a big set of text. Maybe you're trying to tokenize, Shakespeare's plays, for example, or whatever it is, especially in things like natural language processing. Then you have a lot of strings that have a lot of repetition. So instead of creating a new object for each occurrence of the word the, for example, if you intern everything, then every string the is actually going to point to the same object in memory, and you're going to reduce your memory overhead. So there might be a memory optimization here that you may want to use string interning for. Of course, it also is going to help speed up comparisons. Now, when you're trying to find or compare a string against another string, if you know that both strings have been interned, you can use the is operator instead of the equals operator, which will be much faster. So if you've got lots of string comparisons going on, then it might make sense to do some string interning. But in general, unless you actually find that you need it, don't do it. Don't start, interning strings right off the bat. Just use strings normally, and then if you find that you need to speed things up or you need to reduce your memory footprint, depending on the circumstances you're working with, then start doing and looking at string interning. So don't optimize things until you need to actually optimize them. Okay, so let's take a look at some code and see how all this works in practice. So let's take a look at string interning in practice. So we'll take two variables, A and B, and this will get interned because hello looks like an identifier. It's a short string for starters, but that doesn't really matter. As long as it looks like an identifier, it will get interned. So if we do that, we can see what the ID of A and B is, okay? And as we can see, they're the same memory address. Now, on the other hand, if we take something like hello world with a space in it, okay, and then we do the same thing with B, then you'll notice when we print the ID of A and the ID of B, that we do not have the same memory address, right? And that's because A and B do not look, or at least those strings, hello world, don't look like an identifier, and they just don't get interned, at least not automatically. So don't count on string interning to happen. Now, why is that important? Well, because now I can certainly compare A equals B, okay, which is true. Now A equals B in this case is going to be false, right? Because hello world is not interned, so the ID of A, the ID of B is different. But if we take this example over here, let's paste it back in, and let's do A equals B. As we can see, A equals B is true, which is as it should be, but A is B is also true because those two strings were interned. So we have, let's say, one more example that I want to show you. A equals, this is a long string that could, oh no space, that's the thing, that could be used as an identifier. It doesn't even have to be spelled correctly. Okay, so this is what A is. Now I'm going to copy that and I'll run that statement and then I'll paste it in and do B as well. Okay, and A is B, it's going to return true. So as you can see, even for a long string, as long as it looks like an identifier, it will get interned automatically. Why is that? Well, because you may very well be using an identifier in your code, right? And maybe it's in a string, and later on you're going to try and find, let's say, a function whose name is whatever's in that string, or a class whose name is in that string. So Python says, well, in case you're going to do that, I'm going to intern those two strings. Okay, so it does that automatically. Now, we don't have to rely on the automatic string interning all the time. We can actually force string interning. So we can do it in this way. We're going to import sys, okay, the sys module. And in order to do a string interning, we're going to have to say a sys dot intern, and then whatever string we want. So in this case, I'll do this hello world that we've seen before. It doesn't get interned automatically. So let's do that. Let's do the same thing for B, sys dot intern hello world, okay, and then C I'm going to make to just hello world itself. And you're noticing I'm creating C after I've created A and B. So let's look at the ID of each of these variables. So the ID of A, ID of B, and ID of C. Okay. Now you'll notice that the ID of A and B are equal, and that is as expected because we have interned that string hello world in both cases. Now for this third one, we just set C equal to hello world, so Python doesn't try to intern the string, even though technically it could, because this is over here, but it doesn't even try. So remember, if you're going to intern your strings, you need to make sure that you intern every instance of that string, okay? Not just the one. You need to intern all of them, right? So now what this means is that if I know that A and B are intern strings, I can certainly test for equality between the two values, hello world and hello world, using the equality operator, the equals equals. But since those strings are interned, I also know that they are going to match if and only if their memory address matches as well, right? Because I've interned those strings. So instead, I can test A is B, which will also return true. Now, what is A is B testing? It is testing the equality of those two values over here, right? Which are two integer values. Very fast test. Okay, it's very fast to test the equality of two integers. This equality operator here, A equals B, on the other hand, is trying to compare this string and this string character by character. And if it runs out of characters and nothing's mismatched, then you have an equal string. So it takes longer to run that kind of comparison. In everyday code, you really don't need to worry about this. But if you are doing a lot of string comparisons, and by a lot, I mean a lot of string comparisons in your code, then you might want to consider string interning. Let's take a look actually at an example. We're just going to do a very kind of quick and dirty benchmark on this. So let's do this. Let's say def compare using equals. We'll take some parameter n. That's going to be how many times we want to run this comparison. Okay. And we are going to first create two strings that are not interned. So a long string that is not interned, and we'll do that times 200. So we've got a long string that is not interned repeated 200 times. That's really a long string that is not interned. Okay, and then B, we're going to make exactly the same thing. Oops. Okay, but we're going to change it and call it B. Okay, so now that we have that, we're going to write a loop. We're going to say for I in range n, so we're going to loop n times basically, and we're going to say if A equals B, and we're not going to do anything, right? Just going to pass. So really, what we're going to do here, right? This function is going to create two strings, and then it's going to run an equality operation between those two strings n times, whatever n happens to be. Okay. So that's that one. Now instead, what we're going to do here, we're going to say compare using interning, and we'll pass it this parameter n. The only difference is that I'm going to just copy all that code over. The first difference is that sys.intern we're going to use here. Okay. So we're going to take the same string that we had before, but we are going to intern it. Okay. And then the other difference is that instead of using equals B, we can get the same result by using the identity operator is, because we know that the two strings are interned, right? So we're just going to check their memory address. Okay. So this is obviously, I mean, in general, you're not always going to be comparing the same string. You're going to want to be comparing different strings and then see when you get equality. But in this case, what I'm really interested in is the speed difference between the equality operator and the identity operator. So we're going to run this, right? Now we're going to have to run this a certain number of times, and then we're going to time it. So we're going to import time. We've seen this before. And then we're going to set start equals time dot perf counter, which is basically a number of milliseconds. Then compare using equals, and we're going to run this. Now let me see exactly how many. I kind of ran this before, And I want a number that's big enough that we'll see a difference, we'll see a substantial difference in the performance of each of those. So as you can see, I wish, so 3, 6, okay, so 10 million times. So we're going to run this comparison here, this A equals B, 10 million times, okay? And once it's finished running, we'll look at our time.perf counter. And perf counter has an underscore. Okay. Perf counter, and then we will print end minus start. Okay. And maybe we'll even print this here saying this is for the equality. Okay. All right. So this is going to run basically that equality operator 10 million times. This is only going to run once, right? Not 10 million times. Just the equality operator. So it's not like we're timing creating, you know, these two strings 10 million times. And the same thing is going to happen here. The majority of the time is going to be taken by these two loops. Okay, so let's run it and let's see what it doesn't like. Compare using equals, compare using equals. Well, I must have a typo, so I'm just gonna, there we go. And now we can run it. That's gonna take a little while. Okay, there we go, 3.939 seconds. Okay, that's how long it took to run. So now we're gonna do the same thing. So we're gonna copy paste. But I'm not going to use copy using equals. We're going to say copy using interning. Okay? So we're going to run it again 10 million times. We'll do a perf counter in the beginning, perf counter at the end, and then we'll take a look at the number of seconds that have elapsed. And there you go, 0.38. So, and that's why I wanted a big number. I wanted to show you kind of a more drastic difference, right, between the two. But still, you can see that when you are doing large numbers of comparisons of strings, you're better off interning, right? And then doing this equality comparison. Now, of course, interning takes a certain amount of time, right? It takes a certain amount of effort to do the interning. So if you're going to be loading, let's say, 10 million strings and comparing each string once, well, I don't know that you're going to gain much speed by doing interning. Right? But if you're loading 10 million strings and you're going to do, you know, millions and hundreds of millions of, you know, comparisons between those strings, then yeah, start considering interning, right? Even if you're loading, you know, 1,000 strings, but you know you're going to do, you know, 5, 10, 15 million comparisons between those strings, right? Then think about string interning. But if all you're going to do is do a one-time comparison between two strings, there's no point in interning then. All right, thanks for watching, and I'll see you in the next video. Hi, in this video we're going to continue our look at Python optimizations, and in particular we're going to look at peephole optimizations, which is just another variety of optimizations that happens. Now these happen at compile time, and of course your Python code gets compiled before it can run. Right? It doesn't get pre-compiled the way a typical, you know, C language, for example, might get compiled into an executable, you know, once it gets linked. This occurs as it's running, but it does compile your code, and it doesn't have to recompile the same bit of code every time that that code runs within the scope, within the context of running your application. Every time you restart your application, it may recompile. But as long as your application is running, once it's compiled a piece of code, it's going to keep using that compiled version of the code. So certain things get optimized. For example, constant expressions. And what I mean by that is, let's say you have a piece of code that assigns this value to a variable, a equals 24 times 60. Now, if that line of code gets executed many, many times during the lifetime of your program, well, it's going to have to calculate 24 times 60 again and again and again. So you might think as a developer, well, heck, if it's going to do that, I'm just going to put the value 1440 in there. But let's say that, your line of code was minutes equals 24 times 60. Well, now, if you read that from a readability standpoint, it's easy to understand that, okay, well, this means the number of minutes in a day, right? 24 hours times 60 minutes. But if you were to store, if you were to say minutes equals 1440, it might not be immediately evident that this is the number of minutes in a day. So it would be better if you could just leave 24 times 60. But for optimization reasons, if this line of code is going to run thousands of times, then you may say, well, I'm going to store 1440. I'm going to write 1440 in there. But in fact, you don't have to do that. Python will actually do that for us. So we can leave our code as 24 times 60, but when Python compiles this line of code, it's actually going to replace it with 1440. It's going to calculate it. Why? Well, this is a constant expression, so it's safe to do that. As your program is running, this line of code, 24 times 60, isn't going to change. It's essentially a constant. And so constant expressions, or expressions that evaluate to a constant, get pre-calculated and stored. Also short sequences. Short sequences, length less than 20, so sequence types, things like lists, tuples, and strings, will also get pre-calculated. So for example, this tuple, 1, 2 times 5, which evaluates to this long tuple here, well, that's less than 20 in length, and so that is also going to get pre-calculated and stored. Same thing with ABC times 3. That evaluates to ABC, ABC, ABC. Again, these are all constants, and it's going to get pre-calculated and stored. Same thing with this one, hello plus world. That is also a constant. Okay, it's a constant string. It's also less than 20 characters, and that will also get pre-calculated and stored. So every time those lines run, it will use the pre-calculated values. It will not rerun or reevaluate the expressions. On the other hand, the quick brown fox times 10, well, that is more than 20 characters, so that will not get stored, right? There's a trade-off between, storage and computation. So how much overhead do you want to have by storing pre-calculated expressions versus the speed? And so Python decides to do the trade-off at 20 characters. Okay, the next type of peephole optimization we'll look at is membership tests. And what I mean by membership test is something like this. If E in this list 1, 2, 3. Now, this list is actually a constant. Yes, lists are mutable, but in this case, this is, your code. This is the string in your code. Well, that is not going to change as your program is running. You don't change, your actual Python code as the code is running. So this is actually a constant expression. Now, if you had like variable names in here instead, that would no longer apply because the variable's values could change, and therefore, this list expression's evaluation could change. So that doesn't apply. But here, this is just a constant. So, when that is encountered, then Python is going to replace the constant mutable expression by its immutable counterpart. So for example, it will transform essentially the list 1, 2, 3 into the tuple 1, 2, 3, which is a little more efficient for membership testing than lists. So lists will get converted to tuples, and sets will get converted to frozen sets, which are the immutable counterpart of sets. And we'll look at sets and frozen sets and lists and tuples in a lot more detail later on in this course. And we're also going to look at this replacement in code just now, just a little later in this video, and that might make a little more sense as to what's happening. But before we do that, I want to talk about set membership. Set membership is much faster than list or tuple membership because sets are basically dictionaries, right? It may not look like it, but sets are basically implemented just like dictionaries are implemented in Python. So it is much faster to do a lookup of a dictionary, right? If I want to see is, if E in the set 1, 2, 3, I want to see if something is in the set, it's a dictionary lookup. But when it's in a list or a tuple, you essentially have to sequentially move through until you find what you're looking for or you don't find it. Okay, so much easier using, kind of hash maps than using lists for membership testing. So if you are ever in a situation in your code where you're writing something like if E in this constant list or this constant tuple, then you should really think hard and probably write it this way. If E in the set 1, 2, 3. Now, if it's a line of code that's going to get executed once and the list is short, yeah, it doesn't really matter. But, if this is code that's going to get executed again and again and again and again, really start thinking about maybe using sets for membership, especially with constant expressions, instead of lists or tuples. So it is more efficient, and we'll look at that in code, and we'll do that right now. So let's start by looking at some of the peephole optimizations with constant expressions. So we'll create a function, let's call it myfunc, and first thing we'll set a equal to, let's say, 24 times 60. Then we'll do b, we'll make that a tuple that's repeated, so times 5, right? So that's going to be the tuple 1, 2, 1, 2, 1, 2, 5 times. So that will be 10 elements. Then we'll say c is equal to some string, let's say abc times 3. Then we'll do another string, we'll do ab times 11. So this is now going to be a string that will be 22 characters long. So that should not get pre-calculated and stored because that is more than 20 characters. And we can look also at another string if you want, the quick brown fox, and we'll do that times 5, let's say. And lastly, we'll look at, let's say, a list containing, maybe A and B, 2 strings, and we'll multiply that by 3. So this will be a list with 6 elements in that list. However, a list is mutable. It's not a constant technically. So that list is not constant. So that also is not going to get calculated. Okay, so we executed that block of code, which means that Python went through and actually compiled it. So now we can look at what are the constants that are associated with that function. So to do that, we can look at this kind of arcane piece of code, and we'll get back into these kinds of expressions when we look at object-oriented programming with the double underscores, and we'll see a lot more functions that have double underscores as well as properties and so on. So in this case, we're looking at this property that contains all the constants that are associated with that function now that it's been compiled. So when we do that, you'll notice that we have, 24, 60, 1, 2, all these are numbers, right, in that code. They're all present. That string ABC is here, the string AB is here. But take a look at 1, 2 times 5. It's actually this right here. So that was pre-calculated, right? The 24 times 60, which is 1440, is right here. So that was pre-calculated as well. You'll find AB and you'll find 11, but you're not going to find AB 11 times because that's too long. So it did not get pre-calculated. Same thing with E. You'll find the quick brown fox is present, but not the quick brown fox 5 times. And then the same thing with the list. It also is not pre-calculated as A, B, A, B, A, B, because that is not a constant expression, right? A list is a mutable object and therefore it's not constant, so Python isn't going to pre-calculate it. Okay, so the next thing we're going to look at is the membership tests. Okay, so what I mean by the membership tests, remember, was using the in operator. So we can go ahead and we can look at myfunc, and we'll pass in, let's say, E, which is going to be the element we want to search for. And if E in, and we'll use the list 1, 2, 3, and then we'll pass. We're not actually going to do anything with it, and we'll run that piece of code. So that function now has been compiled, and we can go ahead and pull up the constants that are associated with that function. And you'll notice that with this membership testing, the list 1, 2, 3 became the tuple 1, 2, 3. So remember, when we do list and sequence memberships, basically, then the people optimizer is going to transform any kind of mutable element into an immutable version of that element when it can. So in particular, lists become tuples. And if we were to do the same thing again, but this time we'll use a set. So we'll use the set 1, 2, 3. Then when we look at the associated constants, you'll see that the set 1, 2, 3 has become the frozen set 1, 2, 3. Again, we'll look at sets and frozen sets in a lot of detail in a later section. Okay, so the last thing that I want to do is kind of a quick and dirty benchmark, if we can call it that. I mean, benchmarks are more complicated. You have to take averages, run multiple times, and so on. We're just going to do some basic timings, basically, on set membership versus, let's say, list membership or tuple membership. And remember what I said in the slides a little earlier, but set membership is very much more efficient than searching inside a list or a tuple or a string for that matter. Okay, so let's take a look at how we're going to do that. Well, we're going to import the string library. We're going to get something out of the string library that I'll show you in a second. We're going to import the time library. We need to do timings. Okay, so let's import those two libraries. Then I want to show you that the string library has some constants that are pre-created for us, like ASCII letters. So if we look at that, it's basically a string, which remember is a sequence type, that contains all the ASCII characters, lowercase and uppercase, in that order, right? So what we're going to do here is we're going to create a few variables. We're going to create one, which is going to be a list, and that list is going to contain the ASCII letters. Then we're going to create a tuple in the same way. We're going to create a tuple, and we're going to create it using the ASCII letters. Now you'll notice that this is I'm using the constructor for the list. The list has multiple constructors, one of which it can handle basically strings. And a string is just a sequence type. But what it does when you pass it inside the constructor, it takes every character in the string and makes it an element of the list. And then same thing with tuple, which is just the immutable version of a list. Now, we can also do that with a set. So we can call the constructor for the set, passing in also this string. Now, we'll look at sets in a lot more detail later. But for now, basically the set constructor is going to do the same thing. It's going to take this sequence of characters and it's going to create a set out of those characters. If there were repeating characters, it would ignore them because sets do not contain repeating characters. Okay, so we've now got each one of those. Let's take a look at what they look like. So the list is basically just the list, right? Let me use the print statement so that will be a little more concise. Okay, so we have the list, then we have the tuple. Okay, so the tuple, it's basically exactly the same, and you'll notice that the order of the elements in the list and in the tuple are basically the same as the order that we had in that string right here, right? It maintains the order, and that's because lists and tuples are ordered sequences. On the other hand, set is not an ordered sequence. So if we look at set, you'll notice that, yes, we have a set, but there's no guarantee on the ordering of the elements inside that set. All the elements are there, not repeated, which they weren't anyway in this case, but they're not repeated, but they're in no particular order, just like a dictionary. Okay, so the next thing we want to do is we want to basically run a test, and we want to time that test, where we're going to look for a character inside the list and the tuple and the set, and we want to see how long it takes to do that. So we're going to write this method. Let's call it membership test, and we're going to pass in n, which is going to be the number of times we want to test for membership, because obviously it goes so fast that if we were just to try and time a single membership test, we wouldn't be able to tell the difference, right? So we're going to just repeat that test many times. And then we're also going to pass in the container, which is going to be what do we want to search? Well, what object do we want to search? And we'll hard code the object that we're searching for, the string that we're searching for. So for I in range n, right, we're going to repeat this test n times, and we're going to say if, and let's pick some letter in here. Maybe we'll pick P. All right, so let's look for P. Actually, maybe let's pick something more in the middle. Let's go with lowercase z. Okay, so if z is in the container, okay, so we're going to look at whatever that container is, and the container could be a string, it could be a list, it could be a tuple, it could be a set, it could be a frozen set. This operator will figure out how to find something in that particular container. And that's one thing you'll notice with Python, and we'll discuss that in more detail in the object-oriented section. But Python is highly polymorphic. So, and that's, you know, in general how you use Python. You don't try and constrain a variable to a specific type. What you're really interested in is a type that's going to have certain properties. And in this case, I don't care what you pass in, you know, as that second container. This function doesn't care as long as it supports the in operator. That's the only thing it needs to support. Okay, but again, we'll get to that in later sections. So if z is in the container, we're just going to pass. We're not actually going to do anything with that. Okay? All right, so let's go ahead and run some tests. So time, perf, counter, that's going to be our start time. Then we're going to run membership test, and we'll do that 10 million times as well. And the first one we're going to look at is the car list. Then we'll do end equals time dot perf counter, and then we will print, and we'll say that this was for the list, okay, and the timing was therefore end minus start. That will give us the number of seconds that elapsed. So let's go ahead and run that. It will take a little while to run. Well, if I membership test, helps if I spell correctly. Okay, so let's let that run. Okay, so finished running, took 5.3 seconds. So I'm going to copy this entire list, this entire chunk of code, and now instead of doing the membership test in the list, we're going to do it in the tuple. So this will be the timing for tuple, and let's run that. And 5.31. So, you know, I mean, again, this isn't the benchmark, but it's about the same, maybe a little faster, but it could be a little slower in some cases too. It's about the same, okay? And let's go ahead and run it once more. But this time we're going to look at the set, and this will be our set. Let's run that, and as you can see, it takes half a second. So really, as you can see, a lot faster doing set membership than doing tuple or list membership. So whenever you can, prefer using set membership. All right, thanks for watching, and I'll see you in the next video.
Yeah.